Please subscribe to support the channel. The universe is alive. Energy goes in, order comes out. Does that break physics, or is that the operating rule? Because you can measure the gradient that runs the show. The cosmic microwave background sits near 2.725 Kelvin. Most stars range from about 5,000 to 50,000 Kelvin. That difference is free energy that can do work. Across roughly 13.8 billion years, it has powered structure to appear. Galaxies, stars, planets, climates, chemistry, and you, all riding a flow from hot to cold, from concentrated energy to waste heat. And that flow, not luck, explains why complexity shows up and sticks around. Total disorder still rises, but local order grows. You burn fuel and dump heat, yet stable patterns form and persist. None of this violates thermodynamics. It uses thermodynamics. When energy moves from hot to cold, matter can organize while spreading heat. You live inside those organized zones, and you stay there only because the flow keeps going and the gradient stays open. Shut the gradient, the structure fades. Keep the gradient, the structure builds. So here's a test that avoids hand-waving. Take the same checklist NASA uses when it looks for life: metabolism, homeostasis, growth and evolution, and information storage. Metabolism means throughput. Energy in, work done, waste out. Homeostasis means feedback that holds key variables in range. Growth and evolution mean change across time that keeps what works and drops what fails. Information storage means memory written into matter that guides later behavior. Now apply that list to the cosmos, not as poetry, as measurements you can point to, with numbers, uncertainties, and data from telescopes that anyone can check. Start with metabolism because it is the easiest to audit. The universe has a global energy budget tied to how fast it makes stars. Observations across ultraviolet, optical, infrared, and radio light converge on the same curve. Star formation rose from early times to a clear peak about 10 billion years ago. Astronomers call that peak cosmic noon, at a redshift around 2. The rate per unit volume then was on the order of 1/10 to 2/10 of a sun's mass turned into new stars each year per cubic megaparsec. Since that peak, the rate has dropped by roughly a factor of 10 to 20 to today's low value. That is the universe's metabolic history in plain sight. High throughput early, lower throughput now, still running. Why does that matter for complexity? Because throughput sets the capacity for structure. Hot young stars flood their neighborhoods with hard light. Dust absorbs and re-emits that energy. Molecules get pushed into new reactions. Protoplanetary disks heat and cool, clump and clear. Atmospheres on new worlds gain and lose gases. Climates start to run. Oceans, if present, move heat between air and rock. The gradient between hot stars and the cold background powers these processes. Run the flow for millions, then billions of years, and you stack layers of organization, from mineral networks to prebiotic chemistry to ecosystems. Not by miracle, by sustained energy processing. If energy just poured in without control, systems would blow themselves apart. So ask the next question: does the universe show anything like homeostasis? The evidence says yes, through feedback. When a galaxy forms stars too fast, massive stars explode and young stars drive winds, heating and pushing gas out, throttling the next round of starbirth. In the largest halos where gas tries to cool and crash inward, the central black hole switches on, launches jets, carves cavities in the hot plasma, and reheats the gas, stopping a runaway cooling flow. These are not stories, they are measured power inputs. They are repeated, and they stabilize the system around workable ranges. Growth and evolution, same approach. Look for measurable change with selection effects. Small dark matter halos form first, then merge into bigger halos. Gas funnels along filaments, cools and forms stars. Stars forge heavier elements. Those elements seed the next generation of clouds and disks with richer chemistry. Galaxies that regulate inflow and outflow keep making stars for longer. Galaxies that fail to regulate quench earlier. The pattern is clear in surveys. Massive galaxies tend to shut down sooner. Smaller ones keep forming stars later. So you see a mass-dependent evolutionary track, not random drift, a history with winners and losers based on stable fuel cycles and feedback strength. Information storage here is not a metaphor. The cosmic microwave background carries a detailed snapshot of early conditions. Tiny temperature and polarization patterns encode the seeds of later structure with high precision. Galaxies record their own pasts. Metallicity gradients across disks act like ledgers of star formation and mixing. White dwarfs cool in predictable ways, so their temperatures work as clocks that date stellar populations. Even black holes, when you talk about their entropy, imply astonishing information capacity. The key point is simple. The universe writes, keeps, and transmits records across time and scale, and we read them back with instruments. All of this has a price. Entropy rises. Organization is expensive in heat. Stars, galaxies, and accretion disks are efficient entropy makers, and when you total the ledger, black holes dominate the entropy budget by an overwhelming margin. That doesn't kill complexity, it enables it. By dumping entropy into vast sinks, the cosmos maintains the gradients that let small, low-entropy pockets persist and evolve. Your nervous system runs hot for its size and throws off heat to stay stable. The universe does the same at maximum scale. Accelerate the rise of overall entropy, and the side effect is local structure that can compute, adapt, and learn. Put the pieces together and keep it strict. If live means a system that absorbs energy, maintains internal ranges through feedback, grows and evolves, and stores information that guides future behavior, the universe matches a surprising amount of that profile. This doesn't assert purpose, it asserts process. Process that is measurable, falsifiable, and already tracked in sky surveys and spectra. The universe looks less like a static backdrop and more like a running engine that builds and edits structure as it burns gradients. So here's the pressure point you should feel next. If this thing really acts like a living system at scale, where's the wiring? Where are the high-traffic routes that move matter and signals fast enough to coordinate growth and stability? You've seen how brains, power grids, and city networks use hubs and links to do that. The big question is, does the map of the universe show a network that plays a similar role? If the answer lands on yes, even after you account for the different physics and the absurd scale, the claim gets teeth. Does a map of the universe have to look like a brain scan, or are we seeing a real pattern? Because the largest surveys say there's a lattice out there, not a random smear. And you can trace it in 3 dimensions with hard numbers, not vibes. Redshift surveys like SDSS, BOSS, and eBOSS charted millions of galaxies stacked across billions of light years, and the picture that falls out is a filament void network, long threads, big nodes, huge empty bubbles between them. Inside the observable region, you're looking at on the order of 100 billion to a trillion galaxies, and the arrangement isn't uniform, it's clustered, it's connected, it has scale, and you can measure that scale with standard tools. If that sounds like a bold claim, ask the simple question: how do we know it's a lattice and not a trick of perspective? The answer is redshift plus statistics. Each galaxy spectrum gives a distance. You convert sky positions and redshifts into a 3D catalog. Then you compute correlation functions and power spectra. You look for the excess over random. You see the bump at the baryon acylation scale. You see the slope that comes from gravity pulling structures together. And when you visualize the catalog, you get filaments threading clusters with voids in between that run to tens of megaparsecs. This is not a photograph, it's a measurement-driven map, and independent teams get the same answer. So here's the eyebrow raiser. Do the network metrics line up with what we see in neural tissue, or is that just pattern seeking? Researchers have built graphs from both systems and compared them after rescaling. They check the degree distribution, how many connections each node has. They check clustering coefficients, how triangles of links pile up. They check modularity, whether the graph splits into communities. And in several studies, those summary numbers land in similar ranges. Not identical, not proof of shared origin, but similar enough to flag convergence. The underlying physics is different, gravity and hydrodynamics here, electrochemistry there. But the math you use to describe sparse, modular, small world-like graphs can spit out similar signatures. Does that mean the universe thinks? No, it means complex networks under pressure to move stuff efficiently often end up with hubs and corridors. And that brings us to the physics of the filaments, which is not decoration, it's the actual transport layer. Dark matter collapses first, building a scaffolding of invisible mass. Baryons, the ordinary stuff, fall into those potentials. As gas streams in, it shocks, heats, and partially ionizes. Typical post-shock temperatures land between 100,000 and 10 million Kelvin. That hot, thin medium is hard to see directly, but it leaves fingerprints. In ultraviolet, you catch highly ionized oxygen and neon lines. In soft X-rays, you hunt for even higher ionization states. Stack enough background sources, and the absorption tells you there's mass in the filaments, which helps close the missing baryonscape. If there's heat, there must be flow. So ask the next question. Do filaments simply sit there, or do they move matter into the nodes? Simulations and observations point the same way. Gas and galaxies funnel along filaments into clusters. Gravity sets the direction, angular momentum and pressure set the rates. At earlier times, you even get cold streams, narrow, dense feeds that reach deep into massive halos and keep star formation running. Later, as halos grow and heat their gas, the inflow gets shock heated and regulated. Either way, the filament is an active channel, not a static strut. It delivers material, and it also moves momentum and indirectly information, because where mass goes, potential changes. Star formation responds, black holes wake up, feedback fires, and signals propagate down the network in the form of heating, outflows, and change accretion. So what? Why care that the shape looks neural if the physics is different? Because architecture controls performance. In brains, highways and hubs cut the cost of communication and stabilize function. In the cosmic web, hubs and corridors cut the cost of moving mass and stabilizing growth. Similar graph statistics can pop out of very different micro rules when both systems are optimizing flow under constraints. The payoff is practical. The network sets the timetable for when galaxies get fuel, when clusters light up, when feedback must kick in, and how quickly large-scale changes ripple across environments. Topology isn't just an image, it's the backbone that sets rates and limits. If the map is wired for flow, the next pressure point is obvious. What keeps the flow going for billions of years without burning the network down? You need a driver, you need gradients, and you need feedback that stops runaway behavior. That's a non-equilibrium problem, not a static one, and it points straight at the core mechanism that living systems and galaxies both rely on: dissipative structures that stay organized by dumping heat. The question becomes blunt. Is the universe just arranged, or is it actively running on energy streams that maintain that arrangement? Because if it's the second, the stakes go up fast. If everything trends toward disorder, why do hurricanes, cells, and galaxies keep appearing as clean, repeatable patterns again and again in a universe that is supposed to smooth out? The short answer is flow. When energy moves through matter, structure forms, not because matter prefers order, but because open systems, driven by gradients, settle into organized states that shed energy faster. Physicists call these dissipative structures. You've seen them in a pot of water that starts making steady convection rolls. You see them in a cyclone that stabilizes around an eye. And you see them at cosmic scale where hot, bright sources sit next to a very cold background. The cosmos is the biggest non-equilibrium system you'll ever deal with, and it runs on the difference between hot stars and cold space, between concentrated energy and the 2.7 Kelvin microwave glow. Here's the working logic. You supply energy from a high-temperature source. You connect it to a cold sink, and you leave the tap open. Matter organizes into channels that move that energy efficiently. The channels are not decorations, they are the state that the system picks because it moves more energy with less resistance. Shut the flow, the pattern dissolves. Keep the flow, the pattern persists. That's why spiral arms, rings and disks, and stable jets are common, not rare. They are efficient outlets in a universe that is constantly trying to dump energy into the background as quickly as the rules allow. Now treat star formation as metabolism. Step by step, gas in a dark matter halo cools by radiating light. Cooler gas loses pressure support. It fragments into denser clumps. Gravity squeezes those clumps until fusion lights. Each newborn star becomes a compact furnace, taking low-entropy nuclear fuel and turning it into outward radiation and expanding shells of heated gas. The overall entropy of the universe climbs, but inside the neighborhood around that star, you get room for low entropy chemistry to operate. Dust grains grow, ices cycle, complex molecules assemble on surfaces and in warm pockets. Planets form in the same disks that feed the star. And some planets keep long-lived atmospheres that run climate loops for billions of years. This is the same throughput logic you use to describe a cell. Fuel in, work done, waste out, just with gravity and fusion doing the heavy lifting. You can watch the throughput directly, not by guesswork, but by adding up the light where it matters. Ultraviolet light tracks young, massive stars. Infrared light tracks dust that absorbs starlight and re-emitted it. Radio tracks free and synchrotron from star-forming regions. When you combine these bands, you get a map of energy processing per unit volume, plotted across cosmic time. That curve rises from early times, hits a clear maximum about 10 billion years ago, then declines to the present. That is the Maddow-Dickinson star formation history. It's the universe's metabolic rate as a function of age. High early, lower now, but immiscibly non-zero, which means the engine still turns, slowly, steadily, adding small increments of structure each gigayear. The flow would blow systems apart if there were no brakes, so you look for self-regulation, and you find it in every well-studied scale. If a galaxy turns too much gas into stars too fast, supernova and stellar winds kick material out, heat it, and reduce the next round of starbirth. If a massive halo tries to cool its hot gas all the way to the center, the black hole at the core wakes up, powers a jet, chops holes in the surrounding plasma, and reheats the gas. Cooling slows, inflow pauses, and the system avoids a runaway. Dial the gas back down, the jet fades, cooling resumes, and star formation restarts. The loop repeats. It's negative feedback, not intense, but on a plot you can see how it locks variables into workable ranges. Gas supply, temperature, pressure, star formation efficiency, accretion rates, all of them oscillate within bands instead of racing to extremes. Non-equilibrium explains why galaxies don't settle into a single final form. Inflows along filaments, outflows from stars and black holes, and recycling through halos make a cycle, not a straight line. Material that leaves in a wind can cool and return on a timescale of hundreds of millions to a few billion years. Refresh gas changes the star formation rate, the metal content, and the disk stability, which feeds back into how efficiently new stars form. The result is a controlled churn with real memory because each round writes metals and heat into the environment that the next round must handle. That is how you get diversity: quenched ellipticals, blue spirals, dusty starbursts, and quiet dwarfs, all sharing the same basic playbook but running it at different settings. If you like clean tests, align the observable levers with the story. Luminosity densities in ultraviolet and infrared tell you the current throughput. The slope and peak of the star formation history tell you how the engine evolved. The gas fractions and disks tell you how much fuel is on hand. The X-ray brightness of halos tells you how fast cooling should proceed. The presence of cavities and shocks tells you how much energy was injected by feedback. And the ratio of stellar mass to halo mass tells you whether the feedback actually kept efficiencies in the narrow observed band. When those numbers line up across surveys and simulations, you're not dealing with a metaphor. You're dealing with a measurable non-equilibrium machine. Here's the takeaway you can say in one breath. The universe does not coast. It burns gradients. It organizes matter to keep burning them. And it installs feedback that stops the burn from destroying the burner. That is the same class of behavior you call life at small scale. Energy in, regulation on, memory kept, adaptation over time. No mysticism needed, just open systems running long enough to find stable flows, and in finding them, building the structures that ride those flows. If non-equilibrium is the driver, the obvious next challenge is control. What sets the thermostat on galactic scales? What turns jets on at the right moment? What keeps clusters from collapsing into cooling catastrophes? And how do those controls stay tuned across billions of years? The answer lives in feedback as homeostasis, with black holes, winds, and hot halos acting as the regulators that hold the line. And if those regulators are real, you should see their fingerprints. You do, in shocks, cavities, outflow rates, and scaling laws that stay remarkably tight. The question now is how far that control goes and what breaks when it fails. How do galaxies stop themselves from growing out of control when gravity keeps pulling gas inward and cooling keeps trying to drop that gas onto the center fast? The answer is blunt. They regulate, and the regulators are the black holes in their cores, not as monsters swallowing everything, but as thermostats that watch the fuel supply, heat the room, and cut the flow when needed. You see the signature in a tight law. The mass of the central black hole tracks the random speeds of stars in the bulge, the m-sigma relation. Bigger dispersion, bigger black hole. That tie is hard to fake. It tells you the galaxy and the black hole co-evolved, and the control channel is feedback. When the black hole eats, accretion lights up. Jets and winds turn on. Those jets carry mechanical power into the halo. They stir, they heat, they raise the entropy of the gas, and star formation slows. You do not have to take this on faith. You can point to cavities in hot plasma and say, there, that is the work. Chandra and XMM Newton have mapped the glowing X-ray gas in clusters and groups, and over they reveal giant bubbles punched into the medium by past outbursts. The radio lobes sit inside, the X-rays dim where the lobes displace the gas, and the physics is simple. It takes energy to inflate those holes against pressure. The estimated injection per episode lands around 10 to the 59 to 10 to the 61 ergs, which is enough to offset the cooling that would otherwise dump cold gas onto the central galaxy. Ripple patterns, weak shocks, and sound waves around the bubbles show that the power is spread through the core, not dumped in one spot. The predicted cooling flows that should form stars at huge rates are choked back to a trickle because the heater is on. Look closely at the duty cycle. You see repeated outbursts, not one-off events. Cavities at different sizes and distances mark multiple episodes over tens of millions of years. The heater toggles on when the gas cools and sinks. It toggles off when the core warms and the fuel thins. Negative feedback in action. The central engine does not need to know the global state. It only responds locally to density and accretion. And because the hot halo couples well to jet power, the response hits the right reservoir, the gas that would otherwise rain down and light a starburst. Instead, the halo holds a higher entropy profile. The temperature and density stay in a band where cooling times lengthen and the collapse stalls. Cold gas is not a bystander in this loop. It is the switch that flips the system, and ALMA has put numbers on that switch. High-resolution maps in carbon monoxide lines show streams, disks, and outflows of molecular gas near active nuclei and in intense star-forming galaxies. When the star formation surges, you measure mass loading factors above 1, meaning the outflow carries more mass per unit time than the galaxy turns into stars, sometimes by several times. That is a strong pushback. It clears or stirs the same gas the galaxy needs to keep forming stars. And because the outflows are multi-phase, hot, warm, and cold, they can couple across scales. You get fountains. Some gas escapes, some falls back on 100 million year timescales, and the next round picks up with a changed inventory. The result is a controlled throttle, not a straight shutdown. ALMA also shows how close to the knife edge these systems live. Narrow, rotating molecular disks can sit within a kiloparsec of the black hole. One gust of feedback and they shear, compress, or disperse. A small drop in heating and they collapse and feed both star formation and the nucleus. That proximity means the loop can react quickly. It doesn't wait a billion years. It can pivot on timescales of a few million to tens of millions of years, which is fast enough to hold galaxies near the observed scaling relations. Too much gas turned into stars, the stellar mass would overshoot. Too little, and disks would stay gas-rich far longer than we see. The observed band is narrow, so the control must be real. Zoom back to cluster scales and ask, does this microphysics add up to a population effect? eROSITA's All-Sky X-ray survey gives you the demographics. Counting clusters as a function of mass and redshift tells you how structure grew, but it also tells you how much non-gravitational energy sits in those halos. Gas fractions, temperature profiles, and entropy cores are not set by gravity alone. Feedback has raised the floor, especially in lower mass systems where heating can move more mass. When you calibrate masses with lensing and fold-in selection effects, the number counts and the internal thermodynamics jointly prefer models that include sustained AGN heating. Cool cores survive, but they are maintained, not collapsing. Non-cool core clusters show stronger past agitation, and the split tracks with radioactivity. The thermostat leaves fingerprints in the census. This regulation story explains several tight relations that would otherwise be a mess. The M-sigma link itself, the connection between stellar mass and halo mass, the weak scatter in hot halo scaling laws once you account for feedback, and the observed drop in star formation efficiency in the most massive halos. Gravity alone would overproduce stars and overshoot the X-ray brightness in cluster cores. Continuous, gentle, but powerful heating fixes both problems at once. Keep the gas from cooling too fast, and you limit the fuel going to the black hole, which limits the heating, which keeps the gas just warm enough. The loop closes, and it stays balanced for billions of years. You can test the failure modes when feedback falls behind. You see bursts, star formation spikes, cold gas piles up, and radio jets switch to a higher power state, carving fresh cavities. When feedback runs too hot, gas densities drop, star formation fades, and the core looks quenched, but not empty, because inflow along the cosmic web never fully stops. The thermostat has to keep working, forever adjusting to supply. That constant readjustment is why the cores of clusters look similar across wide spans of time. Same entropy floors, same cavity energetics, same modest star formation rates compared to the naive cooling flow prediction. If feedback is the thermostat, the next question is the bloodstream. Where does the fuel come from? Where does the waste go? How fast does a cycle turn, and how many times can a galaxy breathe before it starves? You want the full metabolic loop, inflow, outflow, and recycling, measured in gas, metals, and time, because that is the part that decides how many stars you make and what kind of planets you can build. Where does the fuel come from, and where does the waste go? Because if galaxies keep forming stars for billions of years, there has to be a closed loop you can track, not a one-way gulp. Here's the working picture. Low metallicity gas flows in along the filaments of the large-scale structure. It settles into halos, cools, and feeds rotating disks. Stars form, massive stars explode, and black holes flare. And those events drive winds that lift gas, dust, and newly made elements back out into the halo. Some of that material escapes, but a lot of it slows, cools, and falls back. The result is inflow, outflow, and recycling, a measurable cycle that sets how fast a galaxy can keep making new stars. Start with inflow. The supply line is not vague. It is the intergalactic medium moving down gravitational slopes. At earlier times, narrow, dense streams can stay cool while they plunge through a hot halo and deliver fuel straight to the inner regions. At later times, inflow is warmer and shock heated, so it joins the halo reserve before it can condense. Either way, the chemistry tells the story. Incoming gas is metal poor compared to the galaxy, so when it mixes into the disk, it dilutes the metallicity, and you can catch that dilution in spectra as short, sharp drops during bursts of accretion. Orientation studies back this up. Preferred inflow directions line up with galaxy major axes, while outflows tend to blow out closer to the minor axis, consistent with how disks channel pressure and gravity. Now the pushback. Outflows come in two main families, star formation-driven and AGN-driven. Supernovae and massive star winds dump momentum and heat into the interstellar medium, open chimneys, and launch multi-phase gas at hundreds of kilometers per second. Central black holes can push even harder, coupling jets and wide-angle winds to surrounding gas and reaching thousands of kilometers per second. The key metric is mass loading, how much mass leaves per unit star formed. In compact starbursts, you often see values above 1, meaning the system is ejecting more mass than it's locking into stars. In dwarfs, the ratios can be far higher, which is why small galaxies struggle to hold on to their gas. Outflows are not uniform. They're clumpy, dusty, and patchy. And because they're multi-phase, hot, warm, and cold components can drag on each other and spread energy through a wide volume. Recycling ties both ends together. Much of the ejected material doesn't leave forever. It arcs into the halo, radiates, and returns as a fountain. Typical recycling times run from about 500,000,000 to 3 billion years, shorter in denser environments, longer in more massive halos with hotter atmospheres. This matters because it sets the cadence for star formation. Fast recycling means a galaxy can keep a steady gas fraction and a steady star formation rate. Slow recycling means longer lulls and sharper bursts. And the balance depends on the depth of the potential well, the temperature of the halo, and the power of feedback currently active at the center. You do not need to guess at the existence of the reservoir. You can see it in absorption. The circumgalactic medium, the CGM, is the extended, mostly invisible atmosphere around galaxies. The Hubble Space Telescope's cosmic origin spectrograph turned background quasars into backlights and found strong, widespread absorption from ions like hydrogen, carbon, silicon, and especially oxygen in a high state. The result is a census of gas you don't see in starlight. For Milky Way mass halos, the total mass in this multi-phase medium is on the order of 10 to 100 billion solar masses, spread across cool clouds, warm ionized gas, and hotter, more diffuse plasma. This is the fuel tank and the waste sink at once, holding the inflow before it condenses and keeping the outflow while it cools. Metal budgets add the forensic layer. Stars forge heavy elements and hand them to the gas through winds and supernovae. When you plot oxygen abundance against stellar mass, you see a rising trend, the mass-metallicity relation. More massive galaxies are more enriched because they make more metals and retain more of them. The slope and scatter of that relation tighten once you account for star formation rate, because vigorous star formation both produces metals and drives outflows that can remove them. Measure the metallicity of the outflowing gas and you get a fingerprint of past star formation. High metallicity in the wind tells you the galaxy is venting its processed material. Lower metallicity hints that the wind is sweeping up more pristine halo gas. Integrated over time, these flows explain where the missing metals live. A large fraction are not in stars or the cold interstellar medium. They're parked in the warm and hot CGM and the nearby intergalactic medium. You can connect these diagnostics to direct kinematics. Blue-shifted absorption lines in a galaxy's own spectrum mark material moving toward you along the line of sight, common in winds launched toward the observer. Red-shifted lines against a background source behind the galaxy can signal inflow. Stack many systems and the geometric patterns sharpen. Stronger outflow signatures along minor axes, more inflow signatures near major axes, and equivalent widths that scale with star formation rate surface density. All of it consistent with the disk that feeds along the plane and vents perpendicular to it. Timescales and budgets close the loop. Typical molecular gas depletion times at modest redshift land around 1 to 3 billion years, but because recycling returns a significant fraction of ejected gas on similar timescales, the true consumption time, including reuse, is longer. Galaxies with higher masses keep more of their ejecta and recycle faster. Galaxies with lower masses lose more to the intergalactic medium and recycle slower. This simple mass dependence explains why small galaxies stay metal poor and bursty, while big disks grow metal rich and steadier, and why the most massive halos quench when hot atmospheres and black hole feedback keep recycled gas from cooling effectively. Put it all together and you have a measured metabolism. Inputs in metal poor inflow, processing in the interstellar medium and in stars, outputs in multi-phase winds, and storage in the circumgalactic reservoir that doubles as tomorrow's fuel. The cycle is not smooth. It pulses with inflow events, feedback episodes, and fountain returns, but the averages land where the surveys say they should. The galaxy breathes, and the pace of that breath sets the pace of growth. If this is the breath, the next step is the pulse. How fast did the universe as a whole form stars across time? When did it sprint? When did it slow? And what does that timeline say about how long complex chemistry and stable planets have had to work? The answer lives in the star formation history of the cosmos, the rise to a sharp peak and the long decline to now, and it decides whether the lights are still coming on or fading for good. When did the universe hit top speed? And what did that sprint do to everything that came after? You can point to a clear answer on a single plot. The star formation history, sometimes called the Maddow-Dickinson curve. It rises from the early universe, crests hard around the redshift of about 2, then eases down to today. That crest is cosmic noon, a growth spurt when galaxies were forming stars roughly 10 to 30 times faster than they do now. In plain terms, the cosmos ran hot on fuel and turned gas into newborn stars at a furious pace. And that pace set the chemistry, the structure, and the future options for planets and life. First, terms. The quantity you track is star formation rate density. It tells you how many suns worth of new stars form each year in a chunk of space 1 megaparsec on a side. At cosmic noon, that number is high. By today, it's much lower. And the trend is not a guess. It's built from thousands of measurements across time. You do not depend on one wavelength or one correction. You combine multiple channels that respond to the same process. Young stars flood ultraviolet light. Dust in galaxies absorbs that ultraviolet and re-emits it in the infrared. Free radio emission comes from ionized gas around massive stars. Synchrotron radio comes from electrons accelerated by supernova remnants. Line them up, calibrate them on nearby galaxies where you can count stars directly, and the curves agree on the big picture, a sharp peak, then a long decline. Why a peak at that specific era? Gas supply and gravity. At earlier times, there was plenty of cold gas flowing along filaments into young halos. Mergers were common, turbulence was high, disks were thick, and feedback had not yet amplified to its later strength. Everything favored rapid conversion of gas into stars. Later, halos grew massive, shock heating raised the temperature of the infalling gas, black holes matured and began regulating more forcefully, outflows carried metals and energy into the surrounding medium, and the net effect was a throttle. Galaxies still formed stars, but the average rate fell, not to zero, but to a quieter idle. Quenching and downsizing make that decline uneven. Massive galaxies shut down earlier, smaller galaxies keep going longer. You see it in colors, morphologies, and spectra. Big systems move to the red sequence with old stars and little gas, while many low-mass disks stay blue with ongoing star formation. Mass is the driver because deeper gravitational wells collect more gas early and feed central black holes that can heat the halo efficiently later. Environment helps. Dense regions strip gas and accelerate the shutdown, but the mass trend stands even when you control for surroundings. The upshot is a staggered timeline. Giants sprinted early and then rested. Dwarfs jogged for billions of years more. Let's ground it in numbers you can carry. Today, the cosmic star formation rate density is around 1/100th of a solar mass per year per cubic megaparsec. That is not dead, that is steady breathing. The universe is still forming stars in nearby spirals, in small galaxies, in modest starbursts, just not at the fever pitch of 10 billion years ago. If you integrate the curve over time, you get the cosmic stellar mass density, which is the cumulative product of all those past rates minus what massive stars return to gas. That integral shows most of the stars you see today were formed during and shortly after the peak. The present epoch adds a thin layer, not a new wall. Multi-wavelength receipts are the reason you can trust a story. Ultraviolet on its own misses dust-hidden star formation. Infrared on its own can be confused by older stars heating dust. Radio on its own needs calibration to supernova rates, but together they cross-check. Ultraviolet plus infrared gives a dust-corrected total. Radio confirms the same power when dust is thick. Recombination lines like hydrogen alpha provide an independent view at specific redshifts, and gravitational lensing lets you probe fainter galaxies to test the low luminosity end. The methods disagree on details. They land on the same headline. The curve rises, peaks, falls, and the timing of that fall matches the rise of feedback and the decline of easy gas supply. This timeline matters for planets and chemistry. Heavy elements that build rocks, atmospheres, and biology ramped up during the high-throughput era, By the time the rate slid down, many galaxies had already enriched their gas to levels where rocky planets were common. The slower present is not useless. It's a maintenance phase. It keeps making long-lived, lower-mass stars. It seeds new systems with metals made in older stars. It extends the window where stable environments can persist, and it spreads habitable real estate into smaller, calmer galaxies that didn't quench early. The curve also constrains theory. Simulations that include only gravity overshoot. They form too many stars too early. Add stellar winds, supernova energy, and black hole feedback, and the shape snaps into place. The observed peak height, the decline slope, the mass dependence, the gas fractions in disks all line up with intolerances you can calculate. Change the efficiency of cooling or the strength of feedback, and you can predict how the curve would shift. Then you compare with data. If the prediction breaks, the model adjusts. That is why the star formation history is the lifeline. It forces every idea about galaxy growth to pass a quantitative test. So why didn't the curve rebound? Why not a second growth spurt? Because supply stayed tight. Hot halos held onto their heat. Feedback remained active, and the cosmic web moved gas into larger structures where cooling is slower. The engine did not stall. It settled into a lower gear. And that lower gear still builds, still recycles, still lights new suns that will live for tens of billions of years, especially the small red stars that dominate the counts. The universe traded speed for endurance, and endurance is exactly what long-term complexity needs. You now have the pulse, a measured rise, a precise peak, a controlled decline. But a pulse tells you more than pace. It tells you what the engine was making while it ran. The sprint forged the elements that change chemistry, change planets, and change everything that living matter can try. The next step is blunt. Where did the heavy elements come from, and how do we know? Because if you can track the factories and the delivery routes, you can tell when the universe learned new tricks, and how those tricks set the stage for worlds like yours. How do you get rocks, air, and blood from a universe that started with almost only hydrogen and helium? Because that's the hard limit you face at the beginning. Stars have to build everything else, and they do it in steps you can say out loud. Hydrogen fuses to helium in stellar cores. Helium fuses to carbon and oxygen in older, hotter stars. Heavier shells light up in the biggest stars, building neon, magnesium, silicon, sulfur, and more, layer by layer until you hit iron and its neighbors. And there, the yield stops paying. Fusing to elements heavier than iron does not give you energy back, it costs you. So normal burning stalls. If you want gold, platinum, uranium, and many other heavy species, you need a different engine. Fast, violent neutron capture in rare, extreme events. That engine is the rapid process, the R process. A flood of free neutrons slams into seed nuclei so quickly that decay cannot keep pace. The nucleus climbs to very high mass numbers, then decays back towards stable isotopes later. You get whole chains of heavy elements in one burst. Where do you get the neutron flood? Neutron star mergers give you just that. Two dead stellar cores, made almost entirely of neutrons, spiral together, collide, and spit out neutron-rich debris. Some collapsar-type supernovae may also run an R process in their jets or disk winds, but the cleanest, most direct evidence sits with mergers. You saw the proof in 2017. A gravitational wave chirp rolled in. LIGO and Virgo pinned the masses as neutron stars. Telescopes across the spectrum swung to the patch of sky. A short gamma-ray flash fired, and then an optical and infrared glow rose and changed color over days. That glow is a kilonova, light powered by the radioactive decay of freshly made heavy elements. The spectra shifted from blue to red as lanthanide formed. Their messy electron structures raised opacity and pushed the light to longer wavelength. The numbers are not hand-waving. Modeling the light curves and spectra implies that the merger made a few hundredths of a sun's mass in our process material. Plenty to seed galaxies with the rarest elements. The bottom line is simple. You caught a heavy element factory in action, with the clock, the light, and the physics all in agreement. Core collapse supernovae still matter across the periodic table. Massive stars fuse up to iron, then their cores fail. The star implodes. The bounce and the neutrino bath drive the envelope outward, and that shock wave synthesizes and spreads many mid-weight elements: calcium, silicon, iron peak species, and more. Other slow channels tick along at lower energies. The S process in aging giant stars builds strontium, barium, lead, and friends over long times by slow neutron captures and beta decays. So the inventory you stand on is a mix: steady stellar factories for many elements, plus rare cataclysms for the heaviest. Add it up and you move from a simple chemistry set to a toolbox with thousands of stable isotopes, each with different roles in rocks, atmospheres, and biology. If this is real, you should see the fingerprints in galaxies, and you do. Abundance patterns do not lie. Plot oxygen abundance against stellar mass. You get the mass-metallicity relation. Bigger galaxies are more enriched because they make more metals and keep more of them. Go spatial. Map abundances across disks. You see negative gradients, higher metallicity toward the center, lower in the outskirts, because disks build inside out, and mixing, bars, and spiral arms stir that gradient over time. Mergers flatten or kink it, outflows vent metals, inflows dilute them. The slope and shape of the gradient store record of supply and feedback. In dwarf galaxies, low metallicities and high scatter tell you that outflows won, metals left, and recycling was slow. In massive disks, smoother, richer profiles tell you that retention and reuse dominated. The R process leaves a unique trail too. Elements like europium track it. When you compare europium to iron in stars of different ages and metallicities, you can infer how fast the R process sources turned on relative to normal supernovae. Some ultra-faint dwarf galaxies even show wild star-to-star variation, a sign that one or two early R process events dominated their entire metal budget. Those data tell you that heavy element factories are rare, powerful, and unevenly distributed, but given enough time, mixing spreads their products through larger systems, so later generations of stars and their planets inherit a more uniform supply. Planet chemistry follows directly from this enrichment timeline. Rocky planets need refractory elements: magnesium, silicon, iron, aluminum, calcium, and trace amounts of others. Disks around young stars start as dust and gas with a composition tied to the local metallicity. More metals mean more solids per unit gas, faster growth of pebbles and planetesimals, and an easier path to rocky cores. Surveys find a strong correlation between gas giant occurrence and stellar iron content, and a milder but still positive trend for many small planets, especially close-in super-Earths and mini Neptunes. The message is plain. As galaxies enrich, the inventory of rocks, atmospheres, and complex mineralogy goes up, and with it, the range of surface environments you can build. Chemistry also changes how planets run over time. More radioactive elements like uranium, thorium, and potassium raise internal heating budgets, which can keep mantles convecting and dynamos alive longer. More iron shifts core sizes and magnetic shielding. More carbon and oxygen shape what atmospheres look like after the first billion years of escape and outgassing. Telescopes see the upstream side of this in disks. ALMA maps show carbon monoxide snow lines, rings, and gaps, all functions of temperature and composition, which set where different solids pile up and what embryos grow where. The composition of a star tells you, in broad strokes, the ingredients its planet started with, so you can explain why some systems are metal-rich with tightly packed inner worlds, while others lag. None of this requires guessing at intent. The chain is physical and observed. Star formation sets the throughput. Throughputs set the metal yield. Feedback and the baryon cycle set how much of that yield escapes, mixes, or returns. And the result is a universe whose chemistry evolves step by step from simple to capable. The early cosmos could not make granite continents or oxygen-rich atmospheres. The later cosmos can, because the tool set changed. New nuclei opened new reactions, new minerals, new climates, and new biochemical options. The system didn't just persist, it upgraded its parts list, and that upgrade is measured in spectra, in meteoritic isotopes, and in the crust of your own planet. If elements are the parts and spectra are the receipts, the next question is storage and control. Where is the memory? Where are the bits? How do you read the past from today's sky? And how does information move from the early universe to you? Because if the cosmos builds and regulates, it also records in radiation, in remnants, and in correlations that last for billions of years. The only honest move now is to open the ledger. From black hole entropy to white dwarf clocks to the tiny ripples in the microwave background that lock in the starting conditions. Where does the universe keep its records, and how many records can it keep? Because the numbers are not small, they're brutal. Start with the cleanest bound we have, the Bekenstein limit, which links the maximum information in a region to its energy and size. Push that logic to a black hole, and the capacity scales with horizon area, not volume. That area law is why the bit count explodes. Take a black hole 1,000,000 times the mass of the sun, the kind you find at the center of a small galaxy, and you get on the order of 10 to the 91 bits. That is a storage budget you'll never fill with ordinary matter. The catch is obvious. You can't read it like a disk drive. The information is encoded in the horizon's microstates, and in principle dribbles out in Hawking radiation over absurd times. Still, as a statement about capacity, it tells you the void near compact objects can, in theory, hold more state than any lab could hope to manipulate. If capacity is one pillar, clocks are the next. You need reliable timers to date the story you're reading. White dwarfs are excellent for this. Take a sun-like star, let it shed its outer layers, the core left behind is a white dwarf with no fusion. It just cools, slowly, predictably, its temperature and brightness drop on a schedule set by well-understood physics. Build a cooling sequence for a population and you get an age. Do this in globular clusters, tightly bound old star swarms in the halo, and the numbers cluster around 11 to 13 billion years. You're not guessing, you're reading a thermometer that's been ticking since the first generations of stars formed. And those ages cross-check with other methods, like main sequence turnoffs and radioactive dating in meteorites, so you know the timers are not lying. You can push the clock idea further into detail, because not every white dwarf cools the same way. Heavier ones crystallize earlier. Latent heat slows their descent. Neutrino losses matter at the hot end, and convection zones deepen at the cool end. But those complications are modeled and compared with large, clean samples from surveys, so you get not only an age, but an error bar you can trust, which means you can line up multiple clusters, read their formation sequence, and check whether their orbits and chemical signatures match a buildup by mergers. Many do, giving you a timeline of assembly written into the remnants. Now switch from clocks to ledgers. A galaxy disk writes its spending history in composition. Older stars tend to have fewer heavy elements. Younger stars tend to be richer. That age-metallicity relation is not perfectly tight because gas flows, mixing, and radio migration smear the record, but the trend is there. You can also look at patterns of alpha elements relative to iron. Alpha elements come quickly from massive stars that explode. Iron comes later from type 1a supernovae, so a high alpha to iron ratio means fast, early star formation. A low ratio means slower, extended formation. Plot millions of stars. You see two sequences in the Milky Way, a thick disk track with high alpha and older ages, and a thin disk track with lower alpha and younger ages. That split is a logbook of how the disk grew inside out, how gas diluted and enriched, and how stars migrated over time. Gradients across the disk add another line item. Metallicity usually falls as you move outward, consistent with central regions forming first and faster. Bars and spiral patterns stir that gradient. Mergers kink it, and strong outflows can flatten it by moving metals around. Read enough of these profiles across different masses and environments, and you reconstruct who formed stars quickly and quenched, who fed quietly for billions of years, and who got rattled by interactions. The chemistry is durable. It survives long after gas is gone, so it acts as a durable memory of conditions that no telescope ever directly saw. There's also a record frozen in radiation that crossed space almost untouched. The cosmic microwave background is a snapshot of the universe when it was young and hot, and just starting to let light travel freely. Its temperature is almost perfectly uniform, with tiny ripples at the level of 1 part in 100,000. Those ripples are not noise. They are the initial density variations that gravity later amplified into galaxies and clusters. By measuring the angular pattern of those ripples, how strong they are at different sizes on the sky, you infer core parameters of the universe with percent-level precision. How much normal matter there is, how much dark matter, how much dark energy, how fast space was expanding back then, and how the primordial fluctuations were distributed. Polarization data adds more constraints, and together with maps of lensing and the late-time web, ties the opening conditions to the structures you see now. The point is that photons are excellent couriers. They carry information from the last scattering surface to your detectors with minimal scattering, so the picture is clean. And because the pattern encodes acoustic physics in the early plasma, including a standard ruler scale, you can anchor distance measurements and test expansion history. In a strict information sense, the CMB is a high-fidelity message sent once, read by everyone, and used to validate every later claim about how the universe evolved. Add the new messengers that broaden the channel. Neutrinos from supernovae carry timing and energy information straight from the core. Gravitational waves from black hole and neutron star mergers move phase-coherent signals across the cosmos with essentially no absorption, and both are now part of routine astronomy. Each detection adds a line to the ledger because it tags an event with unique parameters you cannot fake with light alone. Masses, spins, explosion asymmetries, ejecta yields, all of which feed back into the chemical and dynamical histories you reconstructed from stars and gas. So the thesis is not poetic, it is operational. The universe writes information into horizons, into the temperatures of quiet remnants, into the chemistry of long-lived stars, and into background radiation that never forgot its origin. It stores those records for billions of years, and it transmits them through photons, neutrinos, and gravitational waves. You read the bits with telescopes and detectors. You cross-check channels, and you turn raw counts into a narrative with tested uncertainty. That is how you move from pictures to evidence, and from evidence to a working model that can fail if the records disagree. If the records are this rich, you should ask how signals move through space today, not just across time. What carries stress, heat, and charged particles through the thin gas between and inside galaxies? What ties distant regions together when gravity is slow and gas is sparse? The next lever is not mass, it is fields. The weak but pervasive magnetism that threads the cosmos and guides energy and particles across vast distances, which means the next step is to map the wires and see how much control they really have. Why does thin, almost empty space steer matter, heat, and high-energy particles like there are hidden rails underneath? Because weak magnetic fields, spread almost everywhere, do the guiding. In normal spiral galaxies, the field strength sits at a few microgauss. In starbursts, it rises to a few tens of microgauss. In clusters, it stays around microgauss levels across megaparsec scales. And out in the intergalactic medium, there are hints of nanogauss fields draped along filaments. These numbers sound tiny, but in low-density plasma, they control how charged particles move. They bend cosmic rays, they shape shocks, and they change how fast heat and momentum can cross a region. Gravity builds the mass map. Magnetic fields wire the pathways. How do you see something you cannot touch? You use polarization, rotation, and synchrotron light as tracers. Radio maps from arrays like LOFAR and MeerKAT pick up linearly polarized emission from electrons spiraling around field lines. That twist, called Faraday rotation, scales with the amount of plasma and the line-of-sight component of the field integrated along the path. Build a rotation measure grid from thousands of background radio sources, and you get a map of field strength and direction changes through the sky. Planck's polarized dust emission gives the complementary picture in our own galaxy, showing how fields thread cold clouds and set the angles that filaments prefer. Together, these data sketch the connective tissue, not just in one place but across huge volumes. If fields are everywhere, where did they come from, and why aren't they vanishingly weak? The answer is amplification. Dynamos turn tiny seed fields into robust structures we observe. Turbulence stretches and folds the field. Rotation organizes it, and differential rotation in disks, faster inside, slower outside, winds it up. This is the mean field dynamo at work. Simulations and observations both point to growth times of a few 100 million to a few billion years to reach present strengths. Galaxies with higher star formation surface density tend to show stronger fields. That trend lines up with the far-infrared radio correlation. More young stars mean more supernovae, more cosmic rays, more synchrotron power, and, through turbulence, a stronger magnetic field. It's a feedback loop. Star formation drives turbulence. Turbulence feeds the dynamo. The field then regulates gas flows that set the next round of star formation. You can watch the dynamo's footprint in ordered patterns. Spiral galaxies show coherent magnetic spirals that often track but do not perfectly match the optical arms. Bars twist fields into characteristic shapes. Edge-on disks reveal X-shaped halos where buoyant loops and outflows drag lines out of the plane. In dwarfs, where rotation is weaker, the field is more tangled, consistent with a turbulent small-scale dynamo dominating. In clusters, structure and mergers tangle fields on larger scales, and you read them via diffuse synchrotron halos and relics, plus rotation measure fluctuations that encode a power spectrum of magnetic turbulence. Fields do more than sit and shine. They shape jets and shocks. In active galaxies, magnetic tension helps collimate relativistic jets over hundreds of thousands of light years, keeping power focused so it can punch cavities in hot cluster gas and regulate cooling. At shock fronts like supernova remnants and cluster merger shocks, fields control particle acceleration. Charged particles bounce across the shock, scatter on magnetic irregularities, and gain energy. That is diffusive shock acceleration. The result is a steady supply of cosmic rays and radio bright rims. Fields also steer how those cosmic rays move afterward. They tend to stream along field lines rather than cross them, launching waves that heat the gas and carry momentum. That transport is a genuine information channel, a way to move energy and pressure signals faster than gas can drift on its own. There is a quieter, equally important role. Fields set the rules for transport. Thermal conduction is very fast along field lines and very slow across them. Viscosity is anisotropic for the same reason. In cluster cores where cooling wants to run away, magnetic geometry can suppress cross-field heat leaks, helping feedback from a central black hole keep the core stable. In galactic disks, fields add pressure support, change when and where clouds collapse, and help launch winds by giving gas something to push against. Reconnection, where field lines break and rejoin, converts magnetic energy into heat and particle acceleration on small scales, adding another valve in the energy budget. Do the numbers tie back to star formation rates and gas conditions? Yes, there are scaling relations. Average magnetic field strength tracks star formation surface density across many orders of magnitude. Starbursts with fierce turbulence show strong, tangled field and thick radio halos. Calmer disks sit lower on both axes. Even the scatter makes sense, because geometry, age, and gas fraction modulate how well turbulence can feed the dynamo. The consistency of these trends across galaxies and redshifts says the mechanism is general, not a special case, and that means you can fold magnetism into the larger non-equilibrium story with confidence. All of this preserves the clean separation you want. Gravity assembles the skeleton. Magnetohydrodynamics sets the wiring and the control gains. When you add fields to simulations, jets stay collimated longer. Shocks accelerate particles more efficiently. Cluster cores hold entropy floors that match observations. And disk winds carry the right mix of hot and cool phases. Leave fields out, and you miss transport, pressure, and heating channels that the data require. If you need one sentence of analogy, keep it tight. Gravity builds the bones. Magnetism wires the nerves. But the follow-up question is harder. If the medium is wired, how does the plasma inside it behave when you stir it? What do turbulence and shocks really do to the energy flow? And how can apparently chaotic motion end up supporting stable, regulated structures for billions of years? The next step is to follow the disorder itself, see how it cascades, and see how it quietly maintains the very order that looks so fragile from the outside. Why does almost empty space act like a machine shop shaping matter into filaments, sheets, and shocks when there's barely anything there? Because most visible matter isn't neutral gas, it's plasma, a gas where atoms are split into ions and electrons. And that change gives the medium electric currents and magnetic fields. Those fields push back on motion, guide charged particles, and let thin regions behave like cables and membranes. In galaxies and clusters and along the cosmic web, you see the same patterns repeat. Narrow strands that carry flow, thin sheets where discontinuities live, and sharp shock fronts where speed turns into heat. This isn't decoration, it's control in a low-density fluid that responds to forces far beyond plain pressure and gravity. You can track the structure from star cradles to cluster cores without changing playbooks. In molecular clouds, turbulence carves filaments where gravity later wins and stars form. In galaxy halos, hot plasma organizes into buoyant bubbles, ripples, and draping layers around rising jets. In clusters, megaparsec-scale shocks wrap around mergers and radio-bright relics sketch the edges. Despite the huge range of sizes, the same self-organization rules apply. The plasma sets up channels for momentum, heat, and particles, and those channels make the next round of organization easier. You get a hierarchy, not a mess. The numbers behind the "it looks similar" claim come from scaling laws. Measure how fluctuations change with size, and you can plot a power spectrum. From cold clouds to hot cluster gas, those spectra tend to align on slopes that sit near familiar turbulence regimes. Close to the classic fluid case in some environments, a bit steeper in others where magnetic tension and compressible motions matter more. The details vary with Mach number, field strength, and cooling, but the plot-to-plot similarity is striking. Different objects, different instruments, similar slopes. That means energy injected at large scales cascades down through a near-universal ladder of eddies and waves before it dies as heat. You don't have to guess about the energy in the cascade. Observations tag it. The Sunyaev-Zeldovich effect measures how hot electrons in clusters punch extra energy into the cosmic microwave background that passes through. Map this SZ signal and you map pressure fluctuations. Compare those maps to X-ray surface brightness fluctuations and you back out density and velocity ripples. Add radio halos, which glow when relativistic electrons spiral in magnetic fields, and you see where turbulence and shocks are accelerating particles right now. The three channels, pressure, density, and synchrotron, cross-check into a budget for turbulent energy and its dissipation rate. On smaller, galactic scales, you can do a similar audit. Velocity spreads and emission lines show random motions in the interstellar medium. Fine structure line ratios in the infrared flag local heating from shocks and dissipation. And diffuse radio emission thickens above disks where cosmic rays and tangled magnetic fields ride buoyant flows. Piece these together, and you get a picture of constant stirring, driven by supernovae, stellar winds, spiral waves, and in central regions by the outbursts of black holes. This is where feedback comes back into focus. Active galactic nuclei don't just heat a single spot. They inject jets and bubbles that seed turbulence across the halo. The energy spreads as waves and vortices, and that slow, volume-filling agitation keeps gas from collapsing too fast. You see it in cluster cores. Entropy floors sit higher than gravity alone would set. Cooling times stretch, and star formation stays modest, even though there's a lot of gas around. Chaos is the control. Small, disordered motions constantly convert large directed power into mild heat distributed over a wide zone. It's homeostasis by chaos, and it works because the plasma channels that energy where cooling is trying to win. Magnetic reconnection adds another valve. When field lines are pushed together and forced to swap partners, magnetic energy turns into heat and fast particles. You watch that happen in the sun all the time, but the same physics scales up. In cluster cores, reconnection at the edges of rising bubbles and in draping layers can bleed energy into the surrounding medium. In galactic halos, it helps break up cold clouds and mix metals into hot gas. Reconnection is intermittent. It spikes and fades, which is exactly what a thermostat needs. Periodic top-ups, not a blowtorch. Transport rules in plasma are anisotropic, and that matters. Heat moves fast along magnetic fields and slow across them. Viscosity does the same. In clusters, this can suppress cross-field conduction, so cooling doesn't short-circuit the thermostat. In disks, aligned fields let winds and cosmic rays escape along the least resistance routes, reducing buildup and stabilizing the star-forming layer. Turbulence then scrambles the geometry just enough to keep any one pathway from dominating forever. The result is a controlled leak of energy and mass, always on, rarely explosive. Once you accept that a cascade turns big injections into gentle upkeep, tight scaling laws stop feeling mysterious. Galaxies with higher star formation surface density pump more energy into turbulence, so they land higher on relations that tie radio power, magnetic field strength, and gas pressure. Clusters with fresher mergers show louder SZ and X-ray fluctuations, stronger radio relics, and more ragged entropy profiles. Quiet systems slide lower. The scatter reflects geometry and timing, not a different game, and simulations that add magnetohydrodynamics, cosmic ray transport, and anisotropic conduction reproduce the same patterns you see in data. Leave those out and cooling runs away, or jets break too fast. This is the practical takeaway. Disorder is not the enemy of structure here. It is the mechanism that keeps structure viable. Turbulence, reconnection, and shocks dissipate injected power in the right places, at the right rates, to stop catastrophic cooling and to keep gas in the state where it can be used again, tomorrow, by star formation. The plasma builds the rails, the turbulence runs the maintenance crew, and together they hold galaxies and clusters in the narrow bands of temperature, density, and pressure that observations demand. If the plasma sets the environment and the cascade sets the maintenance plan, the next question is about output. What does this controlled churn actually build that you could live on? How often do disks turn that managed gas into planets? How quickly do those planets form? And how common are the conditions that let atmospheres stick around? Because if the system really is metabolic, the factory floor should be full of products. And the surveys of exoplanets say exactly that. The universe is running a planet assembly line at scale, and the numbers change what you can expect in your own neighborhood. How many planets do you get per star? Give me a real number. The clean answer from Kepler statistics and test follow-ups is, on average, 1 or more. Not 1 per 100, not 1 per 10, roughly 1 or higher. Small worlds dominate the count. Super-Earths and mini-Neptunes between Earth and Neptune size are the most common class in the galaxy. Our system is weird for not having one. And when you correct for detection bias, you find a high inventory of sub-Earth to Earth-sized candidates on orbits shorter than a few months. Longer orbits are harder to see, but trend lines say the total keeps rising as you include them. Bottom line, planets are the rule, not the exception, and the catalog is still growing fast. You want the number that really matters? How often do you get an Earth-like planet around the Sun-like star in a temperate zone where liquid water could last? The cautious estimate is on the order of a tenth, meaning a few in 10 Sun-like stars could carry at least one roughly Earth-sized planet in the right insolation band. The error bars are wide. They depend on assumptions about the distribution of orbital periods and radii, and on how you handle false positives and missing long-period worlds. But even the low end of reasonable ranges means a huge absolute inventory, because the Milky Way has hundreds of billions of stars. Multiply out, and you're looking at tens of billions of potential temperate rocky worlds in this galaxy alone. Now, tackle atmospheres, because a rock without an atmosphere is a harsh place, and we can already read air on exoplanets. Transmission spectroscopy sees starlight filtered through a thin rim of gas at the planet's limb. Emission spectroscopy reads the planet's own glow when it swings behind the star. Hubble started the game by finding water vapor features on hot Jupiters and hot Neptunes. Spitzer and ground-based telescopes filled in thermal phases. And now, JWST is pulling clear signals of water, carbon dioxide, methane, and carbon monoxide on warm Neptunes and mini-Neptunes. Cloud decks mute some spectra. Haze complicates others, but the detections are solid, repeated, and modeled, and they prove that we can measure chemistry from light years away. No confirmed biosignatures have appeared, not even close, but the pipeline is working, and retrieval methods are maturing fast. Step back to inputs. How fast does a disk give you the raw material to build these worlds? ALMA answers with images. Protoplanetary disks live a few million years on average, from about 3 to 10 million. They do not look smooth. They show rings, gaps, spirals, and crescents. The cleanest interpretation is that young planets, already a few Earth masses or more, are clearing paths and shepherding dust while the gas is still present. We're catching sculpting in real time. The location of snow lines, where some common volatiles freeze, sets pileup zones for solids, and those zones track with temperature and age. So composition and architecture are wired early, and wired by physics you can map. Metallicity links the stellar and planetary sides of the story. Stars with more heavy elements tend to host more giant planets. That correlation is strong. For smaller planets, the trend is milder but real in many samples. More metals mean more solids. Faster growth from pebbles to planetesimals to cores. Faster core growth means a better shot at capturing gas before the disk disperses. That is why compact multi-planet systems of super-Earths and mini-Neptunes are common, and why the inner few tenths of an astronomical unit are crowded in many systems. Migration matters, resonances matter, but the primary driver is simply how much building material the disk had in the first place and how long it stuck around. Habitability is not only about a zone, it is about time and stability. Low-mass stars offer very long lifetimes, but high flare rates and close-in habitable zones complicate atmospheres. Sun-like stars sit in a calmer middle ground. Tidal locking can be fine if the atmosphere moves heat efficiently. Plate tectonics and a magnetic field buy stability, and those depend on composition and cooling, all of which trace back to the disk and the enrichment of the galaxy. The point is simple. As metallicity climbed over cosmic time, rocky planets became easier to make. Atmospheres had more to work with, and the space of possible stable climates widened. We can already check pieces of this with direct numbers. Occurrence rates from Kepler show planets per star at or above 1 when you integrate over radius and period. TESS is nailing bright, nearby systems that we can characterize with radial velocities and spectroscopy. ALMA measures disk dust masses and lifetimes, connecting starting inventories to end products. JWST is measuring atmospheric C/O ratios that hint at where in a disk a planet formed, inside or outside major snowlines. These are not isolated facts. They are linked steps in a short assembly line. Dust to pebbles, pebbles to planets, planets to atmospheres, atmospheres to climates. There are filters. Photoevaporation can strip light envelopes and turn mini-Neptunes into super-Earths. Collisions can reset surfaces and atmospheres. Migration can scramble order. But the net effect does not erase the main result. It adds variety, which is exactly what a factory does when you push different batches through with slightly different settings. The output is diverse, but the throughput stays high, and the total count of potential habitats keeps mounting. Keep the claim precise. The universe does not merely allow habitats, it mass produces them. Disks form fast, planets assemble quickly, atmospheres show up early, and a non-trivial fraction of stars, especially sun-likes and cooler dwarfs, carry small rocky worlds in or near temperate orbits. We do not have a confirmed living atmosphere yet, but the pipeline that would reveal one is live, tested, and improving with every target. If planets are plentiful and air is measurable, the next pressure test is simple and hard at once. Can you prove a living planet without ever touching it? Can you look at its air and say, this chemistry should not sit together unless something is running it? That is the logic of atmospheric disequilibrium. It works on Earth. It failed on Venus and Mars, and it is about to be the rulebook for exoplanets. The question is whether whole planets show feedback like biospheres do, and whether we can read that loop from light alone. How do you spot life without landing? You look for chemistry that shouldn't sit together unless something keeps refilling it. Earth is the clean case. Oxygen sits at about 21% of the air. Methane sits at a few parts per million. Those two gases react quickly. Methane survives roughly a decade before sunlight and oxygen break it down. Yet it's always there, fresh. That means a constant source. And on this planet, the largest source is biology. Wetlands, ruminants, microbes. The disequilibrium is the signal. It tells you a network is doing work to keep the air out of balance, and that is exactly what a living planet does. You don't need fancy math to get the point. If the atmosphere were left to chemistry alone, it would drift toward a quiet state, oxidized or reduced depending on the star and the rocks. Earth refuses to settle. Methane keeps showing up. Nitrous oxide hangs around. Ozone rises and falls with sunlight and weather. The system runs a set of linked cycles that pull, push, and reset composition every season and every geologic era. When you calculate the total distance from equilibrium for the air-ocean system, Earth lands far from the minimum because biology pumps low-entropy molecules up the gradient. Then the environment burns them back down. It's the same energy in, waste out logic you already know, but wrapped around a whole planet. If that sounds like hand-waving, the rock record makes it concrete. The Great Oxidation Event around 2.4 billion years ago changed the entire game. Before it, oxygen was scarce. Iron stayed dissolved in the oceans and dropped as banded iron formations when local oxygen spikes rusted it out. After it, oxygen rose in the air and stayed there. New minerals appeared that only form in an oxidizing world. Sulfur isotopes shifted in a way that marks the start of a different photochemistry. These are not stories, they're fingerprints, and they say that biology flipped the switch big enough to alter climate, weathering, and the mineral inventory of the crust. Once photosynthesis got efficient and burial trapped enough organic carbon, oxygen could accumulate faster than it was consumed, and the atmosphere crossed a threshold into a new, stable regime. That feedback between geology and biology is the key. Oxygen boosts ozone. Ozone shields the surface from hard UV light. Shielding lets more life spread. More life makes more oxygen, but it doesn't run away forever. Weathering of rocks, volcanic gases, and ocean chemistry push back. The system finds a level, not by design, by negative feedback. Too much oxygen and fires become common. Organic matter doesn't accumulate. The rise stalls. Drop oxygen and methanogens expand. Greenhouse gases climb. Temperature and chemistry shift again. The loops hold the whole planet inside ranges where liquid water and complex chemistry can persist for billions of years. Turn that logic into remote sensing and you get a playbook. You don't chase a single life gas. You look for pairs and patterns that scream active maintenance. Oxygen with methane is the classic. Methane with carbon dioxide, but little carbon monoxide is another, because life tends to mop up easy chemical energy that pure geochemistry often leaves on the table. You watch for seasonal changes that line up with a planet's tilt and orbit. You check whether reflected light hints at vegetation-like edges. You search for ocean glint and pressure markers that tell you the surface can even hold liquid water. And you anchor every interpretation to the star spectrum, because ultraviolet output sets how fast gases break down. You also guard hard against false positives and false negatives. Oxygen can build up without life if a planet loses its oceans. Ultraviolet light splits water. Hydrogen escapes, oxygen piles up. That's a dead sign, not a living one. You catch it by checking for massive oxygen dimer absorption, for very dry air, and for a star with a violent youth that likely stripped water. Methane can appear from serpentinization in the mantle, so you look at the balance of methane with carbon monoxide and at the isotopes when possible. Hazes can hide spectral features, so you combine transmission with emission and reflected light, and you look for thermal structure that fits a plausible greenhouse without invoking life. It's not enough to see an interesting gas, you have to rule out simple abiotic supply and slow sinks. Comparative planetology keeps you honest. Venus is almost all carbon dioxide with a bit of nitrogen, trace oxygen, and clouds of sulfuric acid. No sustained disequilibrium, because any reduced gases get oxidized fast in that hot, intense oven. Mars is also carbon dioxide heavy, thin, cold, with small variable methane hints that fade and reappear at parts per million. That variability is debated and could come from geology and sunlight-driven surface reactions. Either way, there is no strong counterweight gas, nothing that stays out of balance for long. Both worlds show you the baseline. Chemistry doing what chemistry does when there's no global network constantly jogging it away from rest. Back on Earth, you can get more granular and see how the signal emerges from many small engines. Forests draw down carbon dioxide seasonally. Oceans outgas and absorb depending on currents. Microbes in soils leak nitrous oxide, and clouds modulate sunlight and temperature. Satellites read these fingerprints globally. Ground networks read them locally, and the whole picture is a layered control system without a central control room. That matters for exoplanets because you won't resolve continents anytime soon. You'll read blended signals and infer the presence of loops from the stability and the phasing of global averages. Now scale the mindset. If a planet can run self-correcting loops that hold temperature and composition in range, can larger systems do the same with their own variables? Galaxies don't breathe oxygen or methane, but they measure their vitals just as clearly. Gas supply, temperature, pressure, and star formation rate. And the loops you've seen, stellar feedback, black hole heating, recycling, act like thermostats and valves to keep those vitals in narrow bands. The analogy is limited, but the structure is real. High throughput drives instability. Feedback pushes back. A stable state emerges. Then external inputs kick it, and the loop restabilizes. The result is long-lived disks, controlled cluster cores, and a slow, steady feed of new stars and habitable real estate. This is why disequilibrium matters beyond the hunt for life. It teaches you to look for active maintenance, not just static pictures, and to judge systems by how far they sit from a lazy, no-work solution. Planets that live far from equilibrium with steady, repeatable signals are the best biosphere candidates. Galaxies that live far from equilibrium with steady, repeatable star formation laws are the best structure factories. Both obey the same class of rules: open systems, energy gradients, feedback, memory. You do not need to lean on optimism here. The tests are clear. Retrieve multiple gases, check for incompatible pairs, look for seasonal and long-term variability, model the star's ultraviolet environment, and beat down every abiotic pathway you can imagine. Only then talk about a biosignature. The field already works that way for giant and warm planets, and it will push even harder as we aim at small, temperate ones. The bar is high, as it should be. There's a final, uncomfortable angle you can't dodge. If entire planets can run themselves using energy and feedback, can intelligence be seen as a specialized layer on top of that? Just another way to manage gradients and move information. Energy use climbs with technological complexity. Waste heat has to go somewhere. Radio leakage, laser flashes, megastructures that glow in infrared, these are all testable. And the current searches have strict null results so far. But that only sets limits. It doesn't close the door. The question waiting ahead is how far up the ladder a species can climb, and what the universe would look like if that climb became common. Because if intelligence is an entropy management strategy, the next challenge is measuring it at scale. How much power does a truly planetary civilization use, and where do we sit today? Start with a silver benchmark, the Kardashev scale. Type 1 means full control of the energy available on a planet. For Earth, that's around 10 quadrillion watts, give or take. Humanity runs at roughly 20 trillion watts. That's 3 orders of magnitude lower. So we are toddlers on the first step. Not incompetence, just early. Our use has climbed for 2 centuries. Our efficiency has improved. Our grids are smarter, but the absolute number is still tiny compared to what falls on the day side from sunlight. and tiny compared to the thermal and chemical gradients of biosphere processes every hour without help from us. That gap matters because physics sets the rules for every rung up the ladder. Power in must become work plus waste heat out. There is no workaround. A Type 1 species turns most accessible planetary flows into controlled work, weather, tides, geothermal, sunlight, and dumps the same order of magnitude back as heat. A Type 2 species captures a major fraction of a star's light, builds megastructures or swarms, and glows in the infrared. A Type 3 would harvest a galaxy's output and would be hard to miss. These labels are crude, but they anchor a simple test. More engineering, more waste heat, more mid-infrared glow than nature alone would make. Have we seen that glow? Surveys have looked. All-sky infrared maps from space telescopes scan for galaxies or individual stars with anomalous mid-infrared excess that can't be explained by dust heating. The results are straightforward. Lots of dusty galaxies, lots of ordinary warm debris disks, no convincing signatures of star-spanning or galaxy-spanning engineering, at least not at the sensitivity and resolution we have now. The null result isn't the end of the story, it sets upper limits. It says that if Type 3 civilizations exist nearby, they're either rare, short-lived, very efficient in ways that still dump heat outside the bands we're watching, or they live in places and phases we haven't sampled well. Direct signals are the other pillar. The Drake equation is not proof, it's a bookkeeping tool. It forces you to lay out star formation rates, planet frequencies, habitability windows, life emergence odds, intelligence odds, lifetimes, and to show where your ignorance sits. On the measurement side, radio and optical searches keep expanding. Narrowband radio looks for the kind of needle carriers no natural process makes efficiently. Lasers give sharp time domain spikes and very narrow spectral lines. Modern arrays scan billions of channels per target and can catch bursts on sub-second timescales. Sensitivity is now good enough to detect transmitters far weaker than 20th century radar at dozens of light years. But again, the published answer so far is simple: no confirmed technosignatures. This absence does not settle the question, because the search volume is still vanishingly small. Think of a cosmic library, where you've checked a few shelves in one aisle, on one floor, in one building of many. Most stars have barely been observed at all. Most of the sky has not been monitored continuously. Most wavelengths are undersampled. And if signals are intermittent, directional, encrypted, or piggybacked on top of normal traffic like broadband noise, we would miss them unless we stare long and process deep. So no detection is a constraint, not a verdict. The Fermi question, where is everybody, sits in that shadow. It's a reminder to quantify the part we've actually searched and to keep raising coverage and sensitivity. You can add non-techno radio signatures to round out the case. Atmospheric industrial gases like chlorofluorocarbons would be glaring on a nearby temperate planet if present at modern Earth levels, but those lines are faint and require exceptional targets. City lights on a night side would be easy to interpret, but are brutally hard to detect at interstellar distances. Coherent laser beacons could stand out if they sweep past us, but duty cycles matter. Megastructures could produce odd light curves as swarms transit their star, yet dust and natural disks make similar signals. Every candidate has astrophysical lookalikes and demands multi-wavelength follow-up before you say technology. Underneath the methods sits thermodynamics. Intelligence is not magic. It's organized information processing and control layered onto energy flows. More complex activity demands more free energy and produces more entropy, whether you're moving bits in a data center or lifting rock in a mine. Landauer's limit anchors the floor for erasing information. Real devices sit above that floor, so the broad prediction is clean. As complexity rises, so does power consumption, and with it, heat signatures, waste photons, and engineered particles moving through space. If you push that logic all the way up the ladder, you expect detectable side effects once a species sustains very high throughput over large areas for long times. So why aren't we seeing obvious beacons or glowing swarms? Several sober options fit the data. First, lifetimes might be short on the scale of astrophysics. 1 million years is long for a civilization and short for a galaxy. Second, preferences may run to low visibility communication, tight beams, fiber-equivalent links in space, or modulation of natural sources. Third, the energy mix could skew to forms that are hard for us to detect at range, or the engineering could be buried under atmospheric windows that we haven't surveyed rigorously. Fourth, selection biases. We target nearby sun-like stars and obvious galaxies, but the real action could be in places we underobserve, like the crowded inner plane or the far side of dusty regions. Even with those caveats, the frame is valuable. It puts intelligence into the same box as every other non-equilibrium system: gradient exploitation and feedback control. As biospheres mature, they tap larger gradients. As tool-using species mature, they tap even larger ones. And while they do, they write their presence into spectra and sky maps as added heat, altered chemistry, or unusual time variability. The more power they manage, the stronger the imprint should be, which is why the silence, so far, is an active piece of data. It pushes models towards either rarity, low duty cycle, or low detectability strategies. You can turn the lens back on us to see the projection. Our current power is dominated by sunlight captured indirectly, by fossil sunlight and fuels, and increasingly by direct solar, wind, and fission. Our radio leakage has dropped as we move to cables and narrow beams. Our orbit has junk and glints that a distant watcher could notice. Our atmosphere has industrial tracers that rose and now are falling. Our waste heat is trivial on planetary scales, but concentrated locally, in cities. In short, our techno-signature is detectable from nearby with modern instruments, but not spectacular across the galaxy. Scale it up by 1,000, then it would be. Scale it by 1,000,000, and you would spot us in mid-infrared on the far side of the Milky Way. Keep the conclusion tight. If intelligence is an entropy management strategy, then as the universe ages and gradients shift, new managers can emerge. Some will stay small, some will climb, a few may saturate local flows, and the rest will flicker. That's a testable claim. Watch the sky for waste heat above dust expectations. Monitor billions of stars for narrowband or ultra-narrowband spikes. Look for odd atmospheric pairs that only industry makes. And be honest about null results and limits. The latter is there. The rungs are defined by physics, and the path from toddler to type 1 is measurable in watts and photons, not in slogans. If the latter is real and the silence persists, another question sharpens. Does selection act beyond biology? Does the universe itself favor constants and conditions that maximize the production of black holes, stars, or information? Because if reproduction and variation can happen at cosmic scales, the story turns from one ladder to many branching paths, and the only honest move is to ask for predictions you can kill or confirm. Does a universe get better at making black holes the way a species gets better at surviving? If its basic constants can vary a little from one generation to the next? That is the core of Lee Smolin's proposal. Black holes are not just endpoints, they are birth canals. Each forms a new expanding region with slightly different constants: gravity strength, particle masses, force couplings, maybe the cosmological constant. If those baby universes inherit tweaks, then the ones whose constants yield more black holes make more offspring. Selection favors parameter sets that maximize black hole production: reproduction, variation, selection, but now written in cosmology's language. Turn that into a test you can actually run. You need a yield function, number and total mass of black holes produced per unit spacetime. Then you ask, if you nudge the constants a little, up or down, do you get fewer black holes than we see with our constants? If yes, in every nearby direction, our universe could sit at a local maximum, consistent with the idea. If no, if you can point to a small tweak that increases black holes, the idea takes a hit. So what do you vary? The gravitational coupling sets stellar masses and collapse thresholds. The strong and electromagnetic couplings change nuclear burning, carbon and oxygen production, and thus stellar winds and mass loss. The neutron-proton mass split affects how much helium you get after the Big Bang, which sets the first generation of stars. The cosmological constant and the initial fluctuation amplitude set how much structure forms before expansion outruns gravity. All of these feed black hole birth rates through the initial mass function, stellar evolution, and collapse outcomes. There is also a specific prediction that got attention. If neutron stars can be very massive, many massive stellar cores would stop at neutron star instead of continuing to black hole. So a universe that wants to maximize black holes prefers a relatively low maximum neutron star mass. Early versions of the idea pointed to an upper limit not far above 1.5 solar masses, but observations now show several neutron stars at about 2 solar masses or a bit more. That weakens that simple lever. Defenders reply that the outcome depends on the nuclear equation of state and on how other constants co-vary. Critics say the cleanest falsifiable edge just dulled. The status is honest. It is not ruled out, it is not confirmed. The sharpest single number test did not break in Smolin's favor. You can widen the check using whole populations. Gravitational wave catalogs give you black hole mass distributions from mergers. Stellar surveys give you how many massive stars formed when metallicity was low versus high. Population synthesis codes map stellar physics to compact remnants. Now you can ask a controlled, quantitative question. Hold a consistent microphysics model, vary one constant by 1 or 5%, rerun the chain from Big Bang nucleosynthesis to star formation to stellar deaths, and count black holes. If any nearby tweak increases the count or the total mass locked in black holes, the local maximum claim is false. If all small tweaks you try cut the yield, the claim holds up another round. Note the trap. This demands careful, linked modeling across epochs because constants affect many steps at once. The cosmological constant is a clean example. Make it too large and structure barely forms. Black holes plummet. Make it too small and you do not obviously raise the yield because you still need the right fluctuation amplitude and cooling to build massive stars. So our small, non-zero value is at least consistent with not obviously suboptimal. The fluctuation amplitude is similar. Make it much smaller and nothing collapses early. Make it much larger and you may fragment too fast and blow out metals and gas. Again, there is a band that seems productive. The question is whether our values sit at a peak inside that band or just somewhere on the slope. That is where the calculation matters more than rhetoric. Status. Straight. This is speculative. The mechanism for a black hole to spawn a new universe is not derived from a complete tested theory of quantum gravity. The space of constants is high-dimensional and correlated. Predictions depend on choices about what varies and what stays locked, and some pointed tests like the neutron star mass ceiling are debated. Still, the framework forces crisp statements. It connects reproduction, variation, and selection to things you can count. And it can, in principle, fail loudly if someone finds a close-by set of constants that makes more black holes than ours while leaving the rest of physics coherent. That's the value. A falsifiable story beats a just-so story. Biology grew up when it moved from hand-picked examples to predictions that could get killed by data. Cosmology should embrace the same culture where it can, even for big, risky ideas. If the universe is alive only in the soft sense of being self-organized and feedback-rich, that's already interesting. But if any part of the claim gestures towards reproduction across black holes, you owe the audience numbers, not nods. Either our constants sit at a local maximum for black hole yield, or they don't, and you can push that question with simulations, surveys, and nuclear physics constraints. Why include this now? Because a live universe language needs risk. Here, the risk is real. Find a modest tweak that raises black hole production, and the selection idea stumbles. Keep failing to find one as modeling matures, and the idea survives another round. Either way, the work sharpens our understanding of how sensitive structure and stellar death are to the knobs of physics, and that alone is worth it. All that said, selection, even if true, needs an arrow to act on. You still have to explain why time has a direction, why the early universe started in such a smooth, low-entropy state that gravity could build everything we see, and how that one-way street sets the stage for gradients, feedback, and evolution at every scale. If the constants are the rules, the arrow of time is the playing field, and the field itself is strange, smooth then structured, calm then clumpy. The next step is to pin down that arrow and the fossils it left behind. Why does time move one way, and why did complex structure need an almost featureless beginning to exist at all? Start with the cleanest measurement we have. The cosmic microwave background is uniform to about 1 part in 100,000. Those tiny ripples are the initial seeds, but the key point is their smallness. A nearly smooth mass distribution means very low gravitational entropy, low enough that gravity had room to do work, to amplify small differences into galaxies and clusters. If the early universe had been highly clumped, the game would have been over before it began. Large structures or even black holes would have dominated too soon, with little room left for a long history. Gravity flips the everyday rule you learn from gases. A box of gas spreads out and mixes. More mixing means more entropy. Gravity adds a channel where clumping increases entropy. Here's the simple picture. A diffuse cloud collapses under its own pull. Potential energy turns into heat, turbulence, radiation, and eventually compact objects. The surroundings warm and the total entropy goes up. Push the collapse far enough and you make black holes, and those carry enormous entropy compared to the gas you started with. While dense regions collapse, the voids between them expand and thin out. That two-sided motion, pockets getting denser, gaps getting emptier, is how the universe raises entropy while building structure, not in spite of building structure. You can still see a ruler laid down in that early smooth era. Before atoms formed, the universe was a hot plasma of photons, electrons, and nuclei. Pressure from radiation fought gravity, and that tug of war sent sound waves rippling through the plasma. When the universe cooled enough for electrons to latch onto nuclei, light decoupled, and those waves froze in place. The result is a preferred separation scale, about 150 megaparsecs in today's coordinates. Look at the clustering of galaxies and you find a small excess probability at that distance. That feature is the baryon acculation imprint. It's a standard ruler because its physical size is set by well-understood early universe physics. Measure its apparent size at different redshifts and you get distances and expansion rates, locked to a yardstick you trust. That ruler is more than a curiosity. It anchors the timeline of structure growth and expansion. Early on, dark matter drove growth. Gravity won locally and the web took shape. Later, another component took over: dark energy. Today, it accounts for about 69% of the cosmic energy budget. Its effect is to accelerate expansion, which stretches space faster and slows the growth of new structures. Big halos still pull matter in, but on the largest scales, the web stops deepening as quickly. The BAO ruler, measured across time, shows that pivot. Slow early acceleration, then a clear shift to faster expansion in the last few billion years. The arrow of time isn't just entropy talk. It is written into a measured expansion history. Put these pieces in one line. Low initial gravitational entropy set the stage. Gravity's clumping raised entropy while making structure. The BAO ruler records the sound of the young universe and lets you track distances with percent-level precision. And dark energy's late push changes the pace at which structures can keep growing. Time's direction is not an abstract idea. It is the scaffold that allowed gradients to appear, feedback to operate, and complexity to stack, layer by layer over billions of years. This framing also explains why now feels special, but isn't a miracle. Early times were too smooth for chemistry and planets. Far future times will be too stretched and too cold for fresh structure. There is a long middle era where gradients are strong, cooling is efficient, and feedback can regulate. That is the window where stars, planets, and biospheres pile up. It is wide in absolute years, but it only exists because the arrow started at a low entropy beginning and because expansion and growth evolved in the sequence we can now map. If the arrow sets initial conditions and the expansion history, the next move is to turn claims about an alive universe into tests, not slogans. You need operational checks that look like lab science. Energy in, variables regulated, information stored, adaptation over time, all tied to data you can plot and break. Can the cosmos clear that bar when you phrase it cleanly, with numbers and failure modes? That's the only way this story keeps earning attention. Do you call something alive only when it has cells? Or do you test the behavior directly? No excuses. Here's the clean rule set you can apply to any scale. Does the system absorb energy? Does it keep key internal variables in range with feedback? Does it store and use information? And does it adapt over time? If you can answer those with measurements, not slogans, you have an operational test, not a vibe. So what can you actually measure today? Start with energy budgets. You total the ultraviolet light from young stars, the infrared light from dust that reprocesses it, and the radio emission from ionized gas and supernova accelerated electrons. Together, they give you throughput. How much power per volume is being pushed through matter. Then you quantify feedback strength. You read X-ray maps for cavities and shocks. You estimate jet power from the work needed to inflate those cavities against pressure. You add wind speeds and mass loading from optical and millimeter lines, and you compare all of it to the cooling rate of the gas that would otherwise collapse. Finally, you track information proxies. Entropy profiles in halos tell you how mixed and heated the gas is. Correlations in galaxy positions and velocities tell you how well initial information survived into late times. And chemical abundance patterns in stars tell you how past events were recorded in matter. Those are direct, testable channels. Now set expectations that can fail. If feedback really is the thermostat, turning it off in models should break the scaling relations you see in data. The stellar mass-halo mass link should blow up in scatter and normalization. Disks should overproduce stars. Cool cores and clusters should collapse into massive starbursts. The star-forming main sequence should lose its tightness, and metallicity relations should skew high because galaxies would trap too many metals. Instead, observations say those relations hold broadly across redshift and mass, once you include measured levels of feedback power. If future surveys find clean, stable systems that violate all of these at once, the homeostasis claim takes a hit. That's the point. You can kill it with data. Make the checks cross-scale so they're hard to game. In the spatial domain, galaxy clustering is close to a power law over wide ranges. The same basic slope class shows up in interstellar clouds and even in cluster pressure fluctuations. In dynamics, turbulence spectra land near universal slopes with predictable shifts when magnetism and compressibility matter. In growth, you see allometric-like scalings, black hole mass versus bulge dispersion, star formation rate versus stellar mass, outflow rate versus star formation surface density, each with limited scatter that only stays tight if regulation is active. Write those as predictions, then test them with new samples. If the slopes or scatters drift where theory says they should not, you adjust the regulation physics or you drop the claim. Push information harder. If the universe stores and uses information, you should see consistent links between early patterns and late structures. You do. The acoustic peak pattern in the background radiation predicts a standard ruler. You measure that same ruler in galaxy maps. Lensing of the background's tiny ripples lines up with the mass distribution inferred from galaxy motions. Age metallicity relations and alpha to iron patterns in stars match the star formation timelines you derive from luminosity densities. If any of these cross links break cleanly, early signals that don't match late maps or chemical clocks that contradict light-based histories, you have a falsification path for the information flows forward part of the story. Turn to time series, because adaptation is about response, not snapshots. Variable active nuclei show a clear relation between driving power and gas state. You see cavity ages, shock spacing, and halo entropy floors evolve in step. Starburst episodes raise outflows, lower gas fractions, and then settle back on the main sequence in predictable windows. Recycling times inferred from metal budgets match the delays you need to keep star formation quasi-steady. If these lags decouple, if power goes in but halos don't heat, if winds blow but metals don't move, if gas recycles on times far outside the observed bands, then the loop story is wrong, and you change it or you drop it. Keep the readout simple enough to track. Dashboard variables should include throughput, measured in luminosity densities, regulation, measured in jet power and wind mass loading versus cooling, storage, measured in entropy and abundance patterns, and adaptation, measured in how quickly those quantities swing and restabilize after a kick. Predict how each responds to a forced change, a merger, a fuel surge, a jet outburst. Then check the sky for systems in those states. If the before, during, after sequence matches the model, you keep the model. If it doesn't, you throw parts away. The method has a built-in brake on storytelling. You don't get to say alive and walk off. You set thresholds. How much power per unit mass counts as metabolism? How narrow the entropy floor range has to be to claim homeostasis? How strong the cross correlations must be to claim memory? How consistent the lags must be to claim adaptation? And you publish the ranges so they can be attacked. The metaphor earns its keep only if the numbers stay inside the rails across new data and new environments. Cross-check with simulations the hard way. Remove feedback and watch the relations fail. Add only stellar feedback and see dwarfs improve but massive halos still go wrong. Add black hole jets with realistic coupling and see cool cores stabilize and stellar masses drop into the observed band. Sprinkle in magnetism and anisotropic transport and watch jet power spread as turbulence instead of a single hotspot. Each addition moves predictions toward the measured trends. This is exactly how an operational definition should work. Each piece earns its place by shrinking the gap between forecast and survey. Bottom line, you can make alive a testable metaphor by tying it to measurable flows, stable internal ranges, durable records, and adaptive responses. If the cosmos keeps meeting those checks while you raise the bar with better data, the metaphor gains weight. If it fails clean tests, you retire it. Either outcome is progress, because you will have replaced hand-waving with a scoreboard. If the scoreboard matters, then the next step is to listen for the pulses that drive it, the fast and slow beats that carry power and information through space-time, from millisecond drum rolls near black holes to billion-year rhythms frozen into the web. If those beats align with the maintenance story, the case tightens, and if they don't, the story breaks. Either way, the tension rises. Do the biggest engines in the universe keep time? And can you read physics straight off their rhythms? Start small and fast. X-ray binaries, a compact object feeding from a companion star, show quasi-periodic oscillations in their X-ray light. The beats land at milliseconds for stellar mass black holes and neutron stars. That's hundreds of cycles per second. The signal isn't a metronome. It wanders, it broadens, but the peak frequency tracks a physical radius near the inner edge of the disk, close to the innermost stable orbit set by general relativity. Change the mass, the beat shifts. Change the spin, the mapping shifts again. You're watching gravity and plasma negotiate in real time, with the disk's turbulence modulating the brightness as hot clumps orbit and shear. You don't need equations to get the picture. Tighter orbits mean faster ticks. Heavier objects mean slower ticks. So when you see a cluster of frequencies, you can back out scale and spin with real, testable uncertainties. Push up in mass and you slow the clock. Active galactic nuclei, black holes millions to billions of times the sun, flicker on timescales from days to years. Their light curves look noisy at first glance, but the noise is structured. Power spectra carry more power at long timescales and roll off at high frequencies, a red noise pattern with a bend. The bend time roughly scales with black hole mass and with accretion rate, which is exactly what you'd expect if large disks carry slow weather and small disks carry fast weather. You also see interband lags. The ultraviolet can lead the optical, X-rays can drive echoes and lower energy bands, all of which fits a simple layout. A hot, compact region near the hole varies quickly and bathes the cooler, bigger disk. The disk reprocesses that light and answers more slowly. Measure enough objects and the timescale, mass, rate plane lines up. Another clock you can read without touching the system. Some beats are not light at all. They're space-time itself ringing. Gravitational wave detectors record clean chirps as compact binaries spiral together. Frequency rises, amplitude rises, and then the signal cuts at merger and dumps into a short ring down. Every stage carries parameters. The chirp rate pins down a particular mass combination. The phase evolution and polarization pattern carry the geometry. The ring down picks out the final mass and spin. If you know the distance independently, you can test gravity. If you trust gravity, you can use the signal as a standard siren to measure distance. In either case, you are pulling hard numbers out of a transient rhythm that lasts seconds or minutes. And because space-time hardly absorbs, those numbers travel clean across the universe. Not every rhythm repeats. Some are fossils. The baryon acoustic feature is the cleanest example. Early on, pressure waves rippled through the hot plasma. When the universe cooled and let light fly free, those waves froze a preferred separation into matter, about 150 megaparsecs today. You don't see a literal oscillation now. You see a small bump in the probability of finding pairs of galaxies at that separation. That beat is a ruler. It fixes absolute scale in late-time maps, and by tracking how big the ruler looks at different distances, you get expansion history without assuming a specific model first. The ruler's existence is a direct tie between the smooth, early clock and the clumpy, late universe. Put the clocks together and patterns emerge. Small, hot flows tick fast. Big, cooler flows tick flow. Variability power shifts with mass and with fuel rate, and correlations across bands encode geometry. You should expect this. Self-organizing, driven systems make characteristic timescales set by orbital periods, thermal times, and sound crossing times. And when feedback is active, those timescales don't drift randomly. They cluster. You can even see families. X-ray binaries map onto active galactic nuclei once you rescale by mass and accretion rate. Their power spectra look alike. Their lags look alike. Their spectral states migrate along similar tracks. The latter holds across 8 or 9 orders of magnitude. These beats are not just pretty diagnostics. They enforce constraints. If accretion disks didn't move heat and angular momentum the way our models say, the power spectra would break, the lags would flip sign, and the scaling with mass would fail. If jets didn't collimate and couple to their surroundings, cavity ages and shock spacings in clusters wouldn't match the times you infer from flicker in the core. If gravitational wave chirps didn't agree with masses you infer from electromagnetic counterparts, the merger anatomy would be wrong. In practice, the matches are good enough that you can forecast behavior. Catch a new active nucleus brightening, and you can guess when and how its spectrum will pivot. Catch a fresh binary black hole chirp, and you can template match it on the fly. You can also hear when regulation slips. If a cool core in a cluster starts to run away, you'll see variability change character in the nucleus. Jet duty cycles shorten, cavity sizes skew, X-ray and radio halos brighten as turbulence ramps up. The heartbeat shifts as the system hunts for a new balance point. In galaxies, a sharp starburst writes a fast, high-amplitude pulse in the infrared and radio that decays on a well-known timescale as massive stars die, while optical and ultraviolet recover more slowly as the disk rebuilds. The multi-band, multi-timescale rhythm is the maintenance log. It says when energy went in, how it spread, and when the thermostat kicked back in. There's a practical payoff. Rhythms turn snapshots into movies. Large surveys that revisit the sky, optical time domain programs, X-ray monitors, and radio synoptic arrays are building variability atlases. Once you have those, you can sort systems by state, not just by mass or brightness. You can catch rare transitions, you can trigger multi-wavelength follow-ups at the right moment, and you can measure response times directly. Lag spectra become routine. Reverberation mapping turns light echoes into size measurements, and standard sirens add distance anchors you can use even when dust or calibration plagues light-based methods. The cross-scale coherence should adjust your intuition. A universe that self-organizes around energy flows will carry rhythms wherever matter or field can store and release energy on repeatable timescales. Orbits and precession write fast clocks. Thermal and viscous processes write slower still. That latter ties back to the earlier claims. Metabolism, homeostasis, memory, and adaptation all depend on how fast you can move power and information, and the clock tells you how fast those moves actually are in the wild. Keep the takeaway tight. Multiscale rhythms are expected when complex flows self-organize. The beats are not decoration, they are constraints. They let you test gravity near horizons. They let you map disks without imaging them. They let you measure distances without standard candles. And they let you watch feedback run at the cadence set by the engine. If the case for a cosmos that behaves alive is going to stand, its pulses must line up with its regulation. So far, they do, and that raises the next, sharper question. If the engines beat on every scale, what happens when you zoom back to the level that sets the conditions you can actually live on, the space between a star and its planets, where disks turn into worlds, where magnetic fields and tides trade energy, and where snow lines write the chemistry of oceans and air? Those links behave like ecosystems, measurable, reactive, and co-evolving, and they decide which worlds get stable climates and which don't. Do stars and planets act alone, or do they change each other in ways you can measure? Start with the factory floor, where worlds form. ALMA images show rings and gaps in young disks. At tens of astronomical units, you see clean lanes carved in the dust. Those aren't pretty patterns, they're early engineering. Embedded planets a few Earth masses and up push material aside, shepherd pebbles, and redirect gas. Kinematic kinks in CO gas maps line up with those gaps. The gas isn't flowing smoothly, it's feeling gravity from newborn worlds. This means sculpting starts fast, while the disk is still rich in gas, and that timing decides what kind of planets you net. Rocky, mini Neptune, or giant, because cores must grow before the gas evaporates. That early sculpting feeds straight into composition because disks aren't uniform refrigerators, they have snow lines, frontiers where common volatiles flip from gas to ice. The water snow line sits a few AU from a young sun-like star. The carbon monoxide line sits farther out. ALMA locates them with tracers that light up where CO freezes out, and those radii move as the disk cools. Inside the waterline, solids are rock-heavy and dry. Outside it, ice loads the pebbles and speeds growth. Cross the CO line and you change the carbon budget again. That's why a planet's carbon-to-oxygen ratio quietly encodes where it formed and how far it migrated. When JWST recovers that ratio in an atmosphere, you're reading a birth certificate written by snow lines. Once planets exist, the star doesn't just shine on them, it drags on them with field and tides, and they answer back. Magnetospheres connect, especially in tight systems. Hot Jupiters moving through dense stellar wind can induce currents along field lines. You see phase-locked signatures in some systems, star spot modulation and activity flares that peak at the planet's orbital phase, not the star's own rotation. Low-frequency radio searches are pushing hard on this because electron cyclotron emission should be bright when fields connect. The point is simple. The interaction is electrical as well as gravitational, and it can heat upper atmospheres, move angular momentum, and tweak stellar activity cycles. Tides set clocks that matter for climate. Close-in planets tidally lock fast. One face permanent day, one face permanent night. That sounds fatal, but it isn't automatically. A thick atmosphere and oceans can move heat, build a warm terminator zone, and keep air from freezing out on the night side. The strength of that heat engine depends on rotation rate and pressure, both set by how the planet cooled and how it lost or kept its gases. Tides also rewrite the star's rotation, especially when a massive planet orbits close. Angular momentum can flow from the orbit into the star, spinning it up, or from the star into the orbit, moving the planet outward. Which path wins depends on the star's age and structure. We can see the outcome statistically. Systems with hot Jupiters often show odd stellar spins and misalignments that betray long tidal histories. We have a direct handle on stellar ages and rotation through gyrochronology. Stars slow as they age because winds carry away angular momentum. Measure rotation from light curve modulations and you get an age estimate. Add a hot Jupiter and the clock can go off by a noticeable amount, either because tides spun the star up or because the planet's gravity changed the star's internal coupling. This matters for habitability around sun-like and cooler stars, because high-energy radiation drops as stars spin down. Calmer stars cook atmospheres less, but magnetic reconnection and flares can still spike, so you want the full time history, not just a snapshot. Mass loss is the other lever in this ecosystem. Close-in planets can blow off atmospheres under intense ultraviolet and X-ray light. We've watched extended hydrogen clouds around hot Jupiters transit in the ultraviolet. Some lose a Neptune's worth of envelope over hundreds of millions of years. That supplies neutral and ionized gas to the system, which can absorb short wavelength light and alter how the star's activity looks to our telescopes. Again, both directions matter. The star drives loss, the planet changes the star's observable behavior, and the loop keeps evolving as the star spins down and the flux drops. Back to snowlines, because they do more than set ingredients. They set traffic. Pressure bumps near condensation fronts trap pebbles, grow cores faster, and create preferred parking spots for nascent giants. That's why rings often sit near expected snowline radii, and why systems can end up with chains of planets and resonances. Later, migration breaks some chains and leaves others intact. The architecture you see today, packed inner worlds, lone hot Jupiters, spread out giants, is a fossil of where those traps sat and how the disk evolved. And that fossil still affects climate billions of years later because giant planets redirect comets, seed oceans with volatiles, and stir impact rates. Magnetism runs through the whole story. Star and planet dynamos can shield or expose atmospheres, tilt auroral ovals, and even couple torque between bodies. Young, rapidly rotating stars throw strong winds and flares. Older stars quiet down. Red dwarfs complicate this with long active lifetimes, so their close inhabitable zones sit in a harsher radiation bath. Measurements of stellar radio and ultraviolet output, combined with models of atmospheric escape and chemistry, tell you whether a given world can hang on to air or will be stripped down to rock and metal. Put the pieces together and you get a literal ecosystem, not in the biological sense, but as a coupled network. Disks feed planets, planets resculpt disks, snowlines set chemistry, chemistry sets atmospheres, atmospheres and cores respond to fields and tides feed back on stellar rotation and activity. The system keeps adjusting until stellar aging shifts the baseline, and the loop settles into a long, slow cruise. The observational proof is the alignment of clues: ALMA rings and gas kinks, phase-locked activity, rotation age anomalies, snowline traced compositions, and migration footprints in orbital spacing and resonance. This framing sets expectations you can check. Young systems should show stronger magnetic and tidal signatures, faster mass loss, and more dramatic disk substructure. Mature systems should show steadier climates, slower rotation, and chemical patterns that match long-term processing. And the mix should change with stellar type, with red dwarfs trading long lifetimes for harsher space weather, while sun-likes offer calmer light but shorter windows. Survey data already line up in that direction, and the next wave of time domain and high-resolution observations will tighten the links. Keep the analogy short and accurate. Stars and planets co-evolve like hosts and microbiomes. The host sets the energy in the environment, the residents process, return, and modulate. No intent, just physics in a loop that stabilizes or destabilizes climates over time. When the loop lands inside the right ranges, you get long-lived surfaces and chemistry that can go complex. When it doesn't, you get scorched rocks or frozen deserts. The difference is measurable. Now, push the tension forward. These loops need fuel: bright stars, cool sinks, active disks, and steady gradients. But the cosmic engine is slowing. Star formation is fading. Gas is getting locked up in long-lived stars and stellar remnants. Feedback and heating keep the remaining gas too warm and too thin to collapse efficiently. And dark energy stretches space so fast that fresh supply from far away can never arrive. Star formation doesn't crash in a single moment. It fades. Across trillions of years, the rate trends towards zero. Red dwarfs, which sip fuel very slowly, will be the last steady lights. Some live for up to 10 trillion years. After they finish, the universe's bright era is over. The long night begins. The population shifts from engines to embers. White dwarfs cool into black dwarfs. Neutron stars and black holes dominate the compact census. The few mergers left are slow, rare, and local. Galaxies and bound groups have mostly merged into single, rounded systems, and everything beyond your gravitational island has slipped over a horizon you can never cross or see again, because accelerated expansion isolates every island from every other. Radiation backgrounds fade. The microwave glow redshifts into wavelengths larger than galaxies, and the last starlight gets swallowed by dust and black holes or redshifted into oblivion. Does matter itself last, or does it crumble? We do not know. Underground detectors have hunted for proton decay for decades and have not seen it. The limits push the mean lifetime well beyond 10 to the 34 years. If protons are truly stable, black dwarfs and cold rocks will persist. If they decay, the decay is unimaginably slow. Whole mountains would take longer than any current age to dissolve. But given enough time, everything made of normal matter would fade into lighter particles and radiation, slow leakage rather than sudden collapse. Black holes write the next chapter, and their clocks are worse. A stellar mass black hole takes on the order of 10 to the 67 years to evaporate by Hawking radiation. A supermassive one, the kind at galaxy centers, can take around 10 to the 100 years or more. During those eons, they slowly eat whatever wanders close. Then, when nothing is left to swallow, they give their mass back as a thin drizzle of low-energy photons and particles. The largest go last, and when they go, a major reservoir of low-entropy structure goes with them. Once the black holes are gone, the picture is simple and bleak. Maximum entropy wins. Gradients vanish. No temperature differences big enough to drive engines. No dense pockets that can be tapped for work. No fresh fuel dropping out of a cooling halo. Just a sparse bath of long-wavelength photons and extremely rare particles coasting in an ever-expanding volume. You can define heat death in plain words. No free energy remains to do sustained work. And with no gradients to exploit, complex structures can't form or persist. That is biological death, scaled to the cosmos. Even before the final fade, the practical limits bite. Accelerated expansion hides almost all galaxies behind a forever horizon. Only your local bound group remains in view. Cosmic archaeology becomes local archaeology. You read the past from one island and simulations, not from new islands coming into view. Background signals that once acted as ledgers, like the microwave relic, shift to wavelengths so long that no practical detector can read them. Clocks and rulers that define cosmology's golden age slip out of reach. But time's on the milestone, so the scale lands. Star formation dwindles to a whisper within about a trillion to a few trillion years. Red dwarfs can burn for up to 10 trillion. White dwarfs cool to near invisibility by roughly a quadrillion years. If protons decay, most remaining normal matter leaks away over timescales that dwarf those numbers. Black holes, depending on mass, evaporate anywhere from 10 to the 67 to roughly 10 to the 100 years or more. After that, you're left with the thinnest possible sea of radiation and stray particles, doing nothing you would call structure. None of this depends on intention. It is just thermodynamics writing the last chapters. The same rules that allowed complexity while gradients were strong also guarantee its end when gradients die. The same feedback loops that stabilize galaxies cannot conjure fuel. They can only manage it. And eventually, there's nothing left to manage. If you insist on the alive framing, the lifespan is incomprehensibly long. The senescence is slow, and the death is cold. That perspective isn't meant to flatten curiosity. It sharpens it, because the only time you can test the alive universe claim is now, while gradients still run and feedback still leaves clean fingerprints. The way forward is not to predict the very end, it's to measure the processes we've been talking about with instruments that can actually break the story if it's wrong. So ask the pointed question: which observatories and surveys can call the bluff? Which datasets can confirm the loops and the information links across scales? And which will expose the weak parts fast? That's the real pressure test, and the next generation of missions is built to deliver it. What data can actually wreck this story or lock it in? Not in theory, in numbers you can plot. Start with the sky mappers built to stress test growth. Euclid is already returning wide, deep imaging in spectroscopy. Roman will add sharper optics and a massive supernova program. Together, they build weak lensing maps that track how matter, not just light, is arranged. Galaxy-galaxy lensing pins halo masses. Cosmic shear traces growth across redshift. And supernova distances anchor the expansion history. The check is blunt. Does the measured growth rate, the F times sigma 8 combo you get from lensing and clustering, agree with the expansion that supernovae and baryon acoustic rulers say you should have? If it does, gravity and dark energy behave as assumed. If it doesn't, either feedback is mismodeled on small scales, or the large-scale rules need revision. Add cluster counts with lensing calibrated masses and you get a second lever. If clusters are lighter than X-ray says, feedback has injected more energy than your models allow. If they are heavier, you overestimated heating. Either way, the thermostat claim can pass or fail cleanly. Roman's time domain power matters too. A huge uniform Type 1a sample tightens the distance ladder, compares directly with standard sirens from gravitational waves, and cross-checks the HO tension. If the distance scale shifts, growth inferences ship with it, and the entire regulation across time picture must be rescanned. No wiggle room. The plots will force a choice: new physics in the background, wrong growth modeling in the foreground, or both. Push to the earliest galaxies with JWST and the coming extremely large telescopes. This is where the feedback model can snap. JWST has already found bright, compact systems in the first few 100 million years. Now, the task is to measure their real efficiencies. You get gas-phase metallicities from rest frame optical lines. You get dynamical masses from line widths and resolved kinematics. You get outflow speeds from blue-shifted absorption and broad emission wings. If star formation efficiencies and black hole growth at redshift 10 are routinely too high for any plausible inflow plus feedback budget, the loop is too weak. If you see strong winds, suppressed gas fractions, and tight mass-to-light ratios even then, the loop was active from the start. ELTs at spatial resolution, letting you map clumps, turbulence, and rotation at kiloparsec scales, and to weigh early black holes directly from broad-line reverberation. If seed black holes are already huge, you either allow super Eddington phases or change seeding. Both are testable. Lock the initial conditions with SCM4 and Lightbird. Polarization is the big lever. If primordial B modes show up at an amplitude in reach, you get a direct measure of the energy scale of inflation. You refine the spectrum of initial fluctuations that seeded everything else, and you cleanly separate lensing B modes from primordial ones via delensing. If B modes don't show up down to incredibly low levels, whole families of early universe models are out. Either way, the seed pattern, which is the starting point for growth and feedback, gets harder boundaries. SCM4 also tightens the lensing map of the entire sky, giving you an independent growth history to compare with Euclid and Roman, plus sharper limits on the sum of neutrino masses and any extra light relics. If NEF or the neutrino mass sum lands off standard values, the downstream structure story must adjust. Wire the medium with SKA, because magnetism and transport sit under every feedback claim. SKA's rotation measure grid, built from polarization of an enormous number of background sources, pushes toward a dense, all-sky map of line-of-sight magnetic fields. Combine that with SKA's low-frequency synchrotron imaging, and you get field strength, topology, and cosmic ray content across galaxies and clusters. The tests are precise. Does magnetic field strength still scale with star formation surface density at high redshift? Do cluster cores show the level of tangled fields needed to suppress cross-field conduction? Do relics and halos trace the turbulence spectra that feedback models require? If the RM grid bends those relations, magnetism plays a smaller role than assumed. If it matches and tightens them, the nervous system claim stands. Tie these facilities together, and the verdict path gets crisp. Step 1. Compare growth from lensing, Euclid, Roman, CMBS4, with expansion from supernovae and BAO. If consistent, background physics looks fine. If inconsistent, quantify where. Small scales point to feedback modeling, large scales point to new gravity or dark energy behavior. Step 2. Check energy bookkeeping at early times with JWST and ELTs. If observed star formation efficiencies, gas fractions, and outflow energetics fall inside the budgets that simulations with feedback predict, the metabolism story holds. If not, the loop is underpowered and needs rework. Step 3. Test magnetism with SKA. If field SFR relation and field pressure scalings persist and Faraday spectrum match predicted turbulence, transport physics in models is on track. If not, revise how energy spreads. Step 4. Fix the initial seeds with CMBS4 and light bird. If the primordial spectrum and any B-mode detection match a simple inflation model, you freeze the starting line. If they don't, you change the seeds and rerun the whole pipeline. Lay out the falsifiers so nobody has to guess. If weak lensing growth demands unphysical feedback to reconcile with expansion, the homeostasis claim weakens. If clusters show cavity powers and entropy floors that cannot offset cooling when measured honestly, the thermostat claim fails. If JWST finds routine early galaxies whose masses and metal yields are impossible to assemble given any reasonable inflow history, the metabolic curve was misread. If SKA shows field strengths and topologies that do not correlate with star formation or do not suppress transport where required, magnetism isn't the wiring we said it was. If CMBS4 and light bird force an initial condition set that cannot evolve into the late-time web without breaking other observables, the entire from seed to structure chain has a gap. Each fail would be specific, public, and fixable only with a change of story. Also, list the confirmers so progress is not vague. Growth and expansion agree within tightened errors. Cluster energetics match cavity work and halo cooling rates over mass and redshift. Early galaxies show measured outflows and efficiencies that land on the same scaling laws we see later. B modes appear or are excluded at levels that cleanly shrink model space. And the magnetism maps keep the field SFR relation straight while delivering conduction suppression in cool cores. That stack would say the flows, the regulators, and the memory are all real, across scales. None of this needs slogans, it needs cross-checks. Euclid and Roman feed CMBS4, JWST and ELTs feed SKA, and the whole network either converges on one self-consistent picture or it doesn't. If the feedback and information metrics keep lining up, the alive metaphor keeps earning its keep. If they don't, we drop it, and we learn something sharper in the process. So the pressure is simple and high. The instruments are online or close, the tests are defined, the win condition and the fail condition are both clear, and the timeline is short enough to matter, ready to call the verdict when the next wave of data lands. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.